Look up at the night sky, away from the city lights, and you'll see them. Thousands of tiny points of light, each one a star, each one a sun like our own, but with its own story to tell. In our vast universe, stars are the storytellers, the architects, and sometimes the strangest entities we can imagine. I'm your guide on this journey through the cosmos, where we'll explore the most bizarre, extreme, and perplexing stars ever discovered. Stars are not just twinkling lights in our night sky. They are cosmic furnaces, nuclear reactors suspended in space, converting matter into energy through processes so powerful they can shine for billions of years. But why are they so diverse? Why do some behave according to our expectations, while others seem to defy the very laws of physics we thought we understood? The simple answer is that stars, like people, have different masses, different chemical compositions, and are born in different environments. Some stars are born alone, while others form in pairs or groups. Some are born in dense molecular clouds, rich with heavy elements, while others form in the sparse outskirts of galaxies. These initial conditions set stars on different evolutionary paths, leading to the incredible diversity we observe today. The life of a star is a constant battle between two forces: gravity, which tries to collapse the star inward, and pressure from nuclear fusion, which pushes outward. This delicate balance determines everything about a star's life, from its brightness to its lifespan, from its color to its eventual fate, and what lives they lead. Some stars burn bright and die young, lasting only a few million years before exploding dramatically. Others, like our Sun, live steady, moderate lives for billions of years. The smallest stars, red dwarfs, can smolder for trillions of years, outlasting nearly everything else in the universe. But today, we're not here to talk about ordinary stars. We're here to explore the outliers, the exceptions, the cosmic oddities that make astronomers scratch their heads and rewrite textbooks. These strange stars exist at the extremes of stellar physics: the densest, the largest, the most magnetic, the most unstable. They push our understanding of physics to its limits and sometimes beyond. Consider a star so dense that a teaspoonful of its material would weigh billions of tons on Earth. Or a star so large that if placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Imagine a star with a magnetic field so powerful it could erase every credit card on Earth from a distance of halfway to the moon. These aren't science fiction. These are real objects in our universe, waiting to be understood. Why do these extreme stars matter? Because they are cosmic laboratories, places where nature tests the limits of physics in ways we could never replicate on Earth. By studying these strange stars, we learn not just about stellar evolution, but about the fundamental forces and particles that make up our universe. The matter inside neutron stars, for example, exists in a state we can never create in our laboratories. Understanding it could revolutionize our knowledge of physics. Strange stars also play crucial roles in the cosmic ecosystem. The most massive stars forge heavy elements in their cores and scatter them across space when they die, seeding the universe with the raw materials for planets and eventually life. The most explosive stellar deaths, supernovae, trigger the formation of new stars, continuing the cycle of stellar birth and death that has persisted since nearly the beginning of time. Think about this for a moment. The iron in your blood, the calcium in your bones, the gold in jewelry, all of these elements were forged inside stars and scattered across space when those stars died. As the astronomer Carl Sagan famously said, "We are made of star stuff." When we study strange stars, we're studying our own cosmic ancestry. The history of astronomy is filled with moments when observations of strange stellar behavior led to revolutionary discoveries. In the early 20th century, astronomers noticed that some stars seemed to pulsate, growing brighter and dimmer in regular patterns. These Cepheid variables turned out to be invaluable cosmic yardsticks, allowing us to measure vast distances across space. Without them, we might never have discovered that the Milky Way is just one galaxy among billions, forever changing our place in the cosmos. Let's take a moment to appreciate just how far we've come in our understanding of stars. For most of human history, stars were mysterious points of light, thought to be fixed to a celestial sphere that rotated around Earth. It wasn't until the 16th century that we began to understand that stars might be distant suns, and it wasn't until the 20th century that we began to understand how stars generate energy through nuclear fusion. Today, we have space telescopes that can observe stars across the electromagnetic spectrum, from radio waves to gamma rays. We have sophisticated computer models that can simulate stellar evolution over billions of years. We can even detect the subtle wobbles in stars caused by orbiting planets. And yet, with all this technology and knowledge, stars continue to surprise us. Consider the case of Tabby's star, formerly known as KIC 8462852. In 2015, astronomers noticed this star was dimming in strange, irregular patterns, sometimes losing up to 22% of its brightness. Nothing in our understanding of stellar evolution could explain this behavior. Some suggested an alien megastructure might be orbiting the star, perhaps a partial Dyson sphere built by an advanced civilization to harvest the star's energy. While most astronomers now believe the dimming is caused by dust clouds, the mystery reminds us how much we still have to learn. Or consider the case of stars that seem to disappear entirely. In 2017, astronomers studying historical sky surveys discovered that a star visible in a 1950 survey had completely vanished by the time the same region was observed in the 1990s. What could make a star simply disappear? Did it collapse directly into a black hole without a supernova explosion? Was it obscured by a dust cloud? Or is there some other explanation we haven't yet considered? These mysteries drive astronomers to build ever more powerful telescopes, to develop new theoretical models, and to push the boundaries of our understanding. The James Webb Space Telescope, which launched at the end of 2021, promises to revolutionize our view of the cosmos once again, peering deeper into space and therefore further back in time than ever before, revealing stars from the very dawn of the universe. When we observe these ancient stars, we're looking at light that has traveled through space for nearly 14 billion years. These stars formed when the universe was less than 1 billion years old, from gas that was almost entirely hydrogen and helium. They were the cosmic alchemists that began the process of enriching the universe with heavier elements, setting the stage for planets, for complex chemistry, and eventually for life. Today's most powerful supercomputers allow astronomers to simulate the lives of stars in unprecedented detail. These simulations reveal the turbulent, complex processes inside stars, the convective currents that mix stellar material, the magnetic fields that thread through stellar interiors, the nuclear reactions that power stellar furnaces. Yet even with all this computing power, some stellar behaviors remain unpredictable and mysterious. In recent years, our understanding of stars has been revolutionized by a new way of listening to them. Just as seismologists use earthquakes to study Earth's interior, astronomers use subtle oscillations in stars, star quakes, to probe their internal structure. This field, known as asteroseismology, has revealed hidden layers, unexpected rotations, and mysterious cores within stars. One of the most surprising discoveries from asteroseismology is that many stars have cores that rotate faster than their surfaces. Our Sun's core, for example, completes one rotation in about 27 days, almost the same as its surface. But in some stars, the core might spin several times faster than the surface, creating complex patterns of internal motion that we're just beginning to understand. The study of strange stars also connects to some of the biggest questions in physics. What is dark matter? The mysterious substance that makes up about 27% of the universe. What is dark energy? The even more mysterious force that seems to be accelerating the expansion of the universe. Could strange stars help us answer these questions? Some theories suggest that dark matter particles might accumulate in the cores of stars, affecting their evolution in subtle ways. Others propose that certain types of exotic stars might be composed entirely of dark matter, While these ideas remain speculative, they highlight how the study of strange stars reaches beyond astronomy into fundamental physics. As we prepare to dive deeper into specific types of strange stars, it's worth reflecting on why we're drawn to these cosmic oddities in the first place. Is it simply scientific curiosity? Or is there something more profound at work? A desire to understand our place in a universe that continually surprises and humbles us? Perhaps it's both. The study of strange stars reminds us that the universe is not just bigger than we imagine, but stranger than we can imagine. It forces us to confront the limits of our understanding and to push beyond them. It connects us to the cosmic processes that, over billions of years, made our existence possible. So join me as we embark on a journey through the strangest stars in the cosmos. From neutron stars with magnetic fields strong enough to distort atoms, to stars so massive they live on the edge of stability, to stars that dance with black holes in a deadly cosmic ballet. Along the way, we'll encounter phenomena so extreme they challenge the laws of physics as we understand them. Our first stop takes us to the remnants of massive stars that have met their explosive ends. Neutron stars, objects so dense they defy comprehension, where the rules of physics as we understand them begin to break down. These stellar corpses, despite being only about 20 kilometers across, contain more mass than our Sun, compressed into a sphere the size of a city. And as we'll discover, they're just the beginning of our exploration into the strange world of extreme stars. Before we dive into neutron stars, let's take a moment to understand how stars are born. Stars form from vast clouds of gas and dust scattered throughout galaxies. These clouds, mostly hydrogen, can span hundreds of light years. Within these clouds, slight density variations can trigger gravitational collapse. As a region begins to collapse, it fragments into smaller clumps, each destined to become a star. As these protostellar clumps continue to collapse, their centers heat up. When the core temperature reaches about 10 million degrees Celsius, hydrogen fusion begins and a star is born. This process converts hydrogen into helium, releasing energy that pushes outward against gravity, stabilizing the star. The mass of the newborn star determines everything about its future. Stars less massive than our Sun burn their fuel slowly and can live for tens or even hundreds of billions of years. Stars like our Sun live moderate lives of about 10 billion years, but the most massive stars, those 8 times more massive than our Sun or greater, live fast and die young, burning through their fuel in just a few million years before meeting catastrophic ends. It's these massive stars that interest us most today, because they're the progenitors of neutron stars, some of the strangest objects in the universe. When such a star exhausts its nuclear fuel, its core collapses while its outer layers are blown away in a supernova explosion. The core, if it's between about 1.4 and 3 times the mass of our Sun, becomes a neutron star. The journey of a neutron star begins with this bang. Literally, when a massive star exhausts its nuclear fuel, the outward pressure that had been keeping it inflated suddenly vanishes. In less than a second, the star's core collapses under its own gravity. The outer layers bounce off this suddenly super dense core and are blown outward in one of the most energetic events in the universe, a supernova explosion. For a brief moment, a single dying star can outshine an entire galaxy of hundreds of billions of stars. The explosion is so violent that it forges elements heavier than iron, scattering them across space where they'll eventually become part of new stars, planets, and perhaps even living beings. Indeed, many of the atoms in your body were once forged in such stellar explosions billions of years ago. But it's what remains after this cosmic cataclysm that interests us today, a neutron star, one of the strangest objects in the known universe. The core of the original star, containing more mass than our Sun, collapses to a sphere just 20 kilometers across. The gravity is so intense that electrons are forced into the atomic nuclei, combining with protons to form neutrons. The result is, essentially, a giant atomic nucleus the size of a city. The The density of these objects stretches the mind's ability to comprehend. A sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth, roughly the weight of Mount Everest. If you could somehow stand on the surface of a neutron star, you would be crushed by a gravitational force 200 billion times stronger than Earth's. A marshmallow dropped from a height of 1 meter would hit the surface at about 7,000 kilometers per second, about 2% the speed of light. Think about that for a moment. A marshmallow, one of the softest, lightest objects you can imagine, would hit with the impact of a meteorite. That's how extreme the gravity is on a neutron star. But gravity isn't the only extreme property of neutron stars. They also spin incredibly fast. When a star collapses to form a neutron star, it retains most of its angular momentum, but is now much smaller. Just as an ice skater spins faster when they pull in their arms, the neutron star spins faster as it collapses. Some neutron stars rotate hundreds of times per second, so fast that points on their equators move at significant fractions of the speed of light. And then there are the magnetic fields. When a star collapses to form a neutron star, its magnetic field gets compressed too, amplifying it to extraordinary levels. The magnetic field of a typical neutron star is around 1 trillion times stronger than Earth's. But some neutron stars, called magnetars, have magnetic fields 1,000 times stronger still, powerful enough to distort the electron clouds around atoms and make the vacuum itself birefringent, splitting light like a prism. These extreme properties, density, rotation, and magnetism, combine to create some of the most bizarre phenomena in the universe. Some neutron stars emit beams of radiation from their magnetic poles. As they rotate, these beams sweep across space like cosmic lighthouses. If one of these beams happens to sweep across Earth, we detect regular pulses of radiation, hence the name pulsars for these particular neutron stars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge University. She noticed a series of regular radio pulses coming from a fixed point in space. The pulses were so regular, arriving every 1.3 seconds, that Bell and her supervisor Anthony Hewish briefly considered whether they might be signals from an extraterrestrial civilization. They playfully labeled the source LGM-1 for Little Green Men. Further observations revealed more such sources, and the true nature of pulsars as rapidly rotating neutron stars was soon established. Pulsars are more than just celestial curiosities. Their incredibly regular pulses make them some of the most precise clocks in the universe. By monitoring slight changes in these pulses, astronomers have been able to confirm Einstein's theory of general relativity and even detect the first known exoplanets, planets orbiting stars other than our Sun. But perhaps the most extreme neutron stars are the aforementioned magnetars. Their magnetic fields are so powerful that they can trigger starquakes, sudden adjustments in the neutron star's crust that release enormous amounts of energy. In 2004, a magnetar named SGR 1806-20 underwent such a starquake, releasing more energy in 1/10 of a second than our Sun does in 100,000 years. The burst of gamma rays from this event measurably ionized Earth's upper atmosphere, despite the magnetar being about 50,000 light-years away, on the other side of our galaxy. Neutron stars also give us a window into the extreme physics of ultra-dense matter. The core of a neutron star is so dense that atomic nuclei are crushed together, forming a continuous sea of nuclear matter. But what exactly happens at these densities is still uncertain. Some theories suggest that at the center of neutron stars, even neutrons might break down into their constituent quarks, forming a state of matter called quark-gluon plasma, which hasn't existed since just after the Big Bang. As we continue to observe and study neutron stars, we're pushing the boundaries of nuclear physics, general relativity, and quantum mechanics. We're exploring regimes of density and gravity that we can't replicate in laboratories on Earth. And we're beginning to understand the role these extreme stars play in the cosmic ecosystem, forging heavy elements and injecting energy into the interstellar medium. In our next segment, we'll delve deeper into the world of neutron stars, exploring their variations and the extreme phenomena they produce. We'll meet pulsars that spin hundreds of times per second, magnetars with magnetic fields strong enough to tear apart atoms from thousands of kilometers away, and binary neutron stars that spiral together in cosmic dances that end in catastrophic collisions, sending ripples through the very fabric of space-time. Stay with us as we continue our journey through the strangest stars in the cosmos. In our previous segment, we explored the incredible diversity of stars and introduced the concept of extreme stellar objects. Now, we're diving deep into one of the most bizarre classes of objects in the universe: neutron stars. Imagine an object with more mass than our Sun, compressed into a sphere about 20 kilometers across, roughly the size of a city. This object is so dense that a teaspoonful of its material would weigh billions of tons on Earth. Its gravity is so intense that light itself bends around it, and its magnetic field is trillions of times stronger than Earth's. This isn't science fiction, this is a neutron star, and it's one of the strangest objects astronomers have ever discovered. The story of a neutron star begins with the death of a massive star. Stars between about 8 and 20 times the mass of our Sun live relatively short lives by cosmic standards, just a few million to a few tens of millions of years. These stellar giants burn through their nuclear fuel at a prodigious rate, their cores becoming increasingly complex as they fuse lighter elements into heavier ones. First, hydrogen fuses into helium, then helium into carbon, and so on, until they develop an iron core. Iron marks the end of profitable fusion. Fusing elements lighter than iron releases energy, but fusing iron or anything heavier actually consumes energy. Once a massive star develops an iron core, it faces an energy crisis. The outward pressure from fusion that had been holding the star up against its own gravity suddenly vanishes. In less than a second, the star's core collapses. The collapse is catastrophic and unstoppable. Electrons, which normally keep atoms from coming too close together due to the Pauli exclusion principle, are forced into atomic nuclei, combining with protons to form neutrons. This process, called electron capture, releases ghostly particles called neutrinos, which carry away vast amounts of energy. The core shrinks from a size of thousands of kilometers to just about 20 kilometers in diameter. As the star's outer layers crash down onto this newly formed neutron core, they bounce back with incredible force, creating a shockwave that rips through the star. Enhanced by the immense neutrino flux, this shockwave tears the star apart in one of the most energetic events in the universe, a supernova explosion. For a brief moment, typically lasting a few weeks, a supernova can outshine an entire galaxy of hundreds of billions of stars. These cosmic explosions are so bright that they can be seen across vast cosmic distances. In 1987, astronomers observed a supernova in the Large Magellanic Cloud, a satellite galaxy of our Milky Way, about 160,000 light-years away. This supernova, designated SN 1987A, was visible to the naked eye, despite being in another galaxy altogether. But what interests us today is what remains after the supernova fades, the neutron star at its heart. A neutron star is in many ways a giant atomic nucleus. In normal matter, atomic nuclei, composed of protons and neutrons, are separated by relatively vast spaces filled with electrons. But in a neutron star, these spaces are gone. The entire star is essentially one massive nucleus, held together not by the strong nuclear force, but by gravity. The density of a neutron star defies comprehension. The human mind simply isn't equipped to truly understand it. Let's try a few analogies. If you could somehow transport a teaspoonful of neutron star material to Earth, it would weigh about 1 billion tons, roughly the weight of Mount Everest. Put another way, a cubic centimeter, about the size of a sugar cube, of neutron star material contains more mass than all of humanity combined. The gravity of a neutron star is equally extreme. On Earth, if you drop an object, it accelerates at about 9.8 meters per second squared. On the surface of a neutron star, the acceleration due to gravity is about 200 billion meters per second squared. If you could somehow stand on the surface of a neutron star, you would be crushed to a thin film, less than an atom thick. A marshmallow dropped from a height of 1 meter above a neutron star would hit the surface with the energy of a nuclear bomb. This extreme gravity creates some fascinating effects. According to Einstein's theory of general relativity, gravity warps spacetime. The intense gravity of a neutron star warps spacetime so severely that light from the backside of the star can be bent around to the front, allowing an observer to see more than half of the star's surface at once. This effect, called gravitational lensing, is even more pronounced around black holes, but it's significant for neutron stars as well. The gravity of a neutron star also affects time itself. Time passes slightly slower in strong gravitational fields, an effect called gravitational time dilation. Clocks on the surface of a neutron star would run about 30% slower than clocks on Earth. This isn't just a theoretical prediction, it's a measurable effect that astronomers have to account for when studying neutron stars. But extreme gravity is just one of the remarkable properties of neutron stars. They also rotate incredibly fast. Some complete several hundred rotations per second. This rapid rotation is a consequence of the conservation of angular momentum. When a star collapses from a size of millions of kilometers to just 20 kilometers, it's like an ice skater pulling in their arms during a spin. The star's rotation speeds up dramatically. These rapidly rotating neutron stars, called pulsars, emit beams of radiation from their magnetic poles. As they rotate, these beams sweep across space like cosmic lighthouses. If Earth happens to lie in the path of these beams, we detect regular pulses of radiation, hence the name pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge University. She noticed a series of remarkably regular radio pulses coming from a fixed point in space. The pulses were so precise, arriving every 1.3 seconds, that Bell and her supervisor, Anthony Hewish, briefly considered whether they might be signals from an extraterrestrial civilization. They playfully labeled the source LGM-1 for Little Green Men. Further observations revealed similar pulsating sources elsewhere in the sky, and the true nature of pulsars as rapidly rotating neutron stars was soon established. Today, we know of thousands of pulsars throughout our galaxy. Some rotate relatively slowly, completing one rotation every few seconds, while others, called millisecond pulsars, spin hundreds of times per second. One of the fastest known pulsars, PSR J1748-2446, rotates about 716 times per second. That means points on its equator are moving at about a quarter the speed of light. Any faster, and the neutron star would be torn apart by centrifugal forces. The incredible precision of pulsar rotations makes them some of the most accurate clocks in the universe. Pulsars typically keep time with an accuracy comparable to atomic clocks on Earth. This precision has made pulsars valuable tools for astronomers. By carefully monitoring the arrival times of pulsar signals, astronomers can detect tiny changes in the pulsar's orbits, allowing them to make groundbreaking discoveries. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a pulsar in a binary system with another neutron star. Over time, they observed that the orbital period of this binary system was decreasing exactly as predicted by Einstein's theory of general relativity. If the system were radiating gravitational waves, ripples in space-time caused by the acceleration of massive objects. This indirect detection of gravitational waves earned Hulse and Taylor the Nobel Prize in Physics in 1993 and provided crucial support for Einstein's theory decades before gravitational waves were directly detected by LIGO in 2015. But the extreme properties of neutron stars don't end with their density and rotation. They also possess incredibly powerful magnetic fields. When a star collapses to form a neutron star, its magnetic field gets compressed too, amplifying it to extraordinary levels. The magnetic field of a typical neutron star is around 1 trillion times stronger than Earth's magnetic field, and 1,000 times stronger than the strongest steady magnetic field ever created in a laboratory on Earth. These powerful magnetic fields shape the environment around neutron stars in dramatic ways. They channel charged particles along field lines, creating beams of radiation that we detect as pulsar signals. They heat the neutron star's surface unevenly, creating hotspots at the magnetic poles. And they can even affect the structure of atoms in the neutron star's atmosphere, distorting electron orbitals and altering atomic energy levels. But some neutron stars, called magnetars, have magnetic fields hundreds or thousands of times stronger still. The magnetic field of a magnetar can reach about 1,000,000,000,000 times the strength of Earth's magnetic field. These fields are so powerful that they can tear apart molecules from thousands of kilometers away, distorting the very atoms that approach them by pulling their electron clouds into elongated shapes. The energy stored in a magnetar's magnetic field is enormous. Occasionally, this energy is released in violent events called magnetar flares. In 2004, a magnetar named SGR 1806-20 underwent such a flare, releasing more energy in 1/10 of a second than our Sun does in 100,000 years. The burst of gamma rays from this event was so powerful that it measurably ionized Earth's upper atmosphere, despite the magnetar being about 50,000 light-years away, on the other side of our galaxy. The origin of these extreme magnetic fields remains a subject of ongoing research. One theory suggests that they result from a dynamo effect during the neutron star's formation, when the core of the collapsing star is rotating very rapidly and is highly convective. Another theory proposes that some massive stars have unusually strong magnetic fields to begin with, and these fields are then amplified during the collapse. As we've seen, neutron stars are defined by extremes: extreme density, extreme gravity, extreme rotation, extreme magnetic fields. But what about their internal structure? What's inside a neutron star? The honest answer is that we don't know for sure. The conditions inside neutron stars are so extreme that they're difficult to model, even with our most powerful supercomputers. But astronomers and physicists have developed theories based on our understanding of nuclear physics and observational constraints. A typical neutron star is thought to have a layered structure. The outer layer, just a few centimeters thick, is a solid crust composed of atomic nuclei and free electrons. Deeper in, as the pressure increases, the atomic nuclei get squeezed closer together, eventually merging into a continuous sea of neutrons with a small admixture of protons and electrons. This material isn't exactly a solid, liquid, or gas. It's a state of matter that doesn't exist anywhere on Earth, sometimes called neutron-degenerate matter. But what happens at the very center of the neutron star, where the density reaches several times the nuclear density, remains uncertain. Some theories suggest that at these extreme densities, even neutrons might break down into their constituent quarks, forming a state of matter called quark matter or quark-gluon plasma. This exotic state of matter may have existed in the earliest moments after the Big Bang, when the entire universe was hotter and denser than the core of a neutron star. Other theories propose even more exotic possibilities. Perhaps the high pressure leads to the formation of condensates of strange quarks or kaons. Perhaps it leads to the formation of a Bose-Einstein condensate of pions. Perhaps it even leads to the formation of a completely new state of matter that we haven't yet conceived of. The cores of neutron stars may be cosmic laboratories where nature explores physics beyond our current understanding. One way astronomers try to constrain these theories is by measuring the masses and radii of neutron stars. The relationship between a neutron star's mass and its radius depends on its internal structure, which in turn depends on the behavior of matter at extremely high densities. By observing neutron stars in binary systems, astronomers can measure their masses with high precision. Measuring their radii is more challenging, but techniques involving the analysis of X-ray emission from their surfaces are providing increasingly precise measurements. Another approach involves gravitational wave observations. When two neutron stars spiral together and merge, as observed by LIGO and Virgo in 2017, They create gravitational waves that carry information about their internal structure. By analyzing these gravitational waves, astronomers can place constraints on the properties of nuclear matter at high densities. The study of neutron stars connects to some of the most fundamental questions in physics. How does matter behave at extreme densities? How do the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, interact under these conditions? The answers to these questions could have profound implications for our understanding of the universe. But neutron stars are more than just physics laboratories. They also play important roles in the cosmic ecosystem. The supernova explosions that create neutron stars scatter newly formed heavy elements across space, enriching the interstellar medium with the raw materials for new stars, planets, and eventually life. The powerful magnetic fields of neutron stars accelerate charged particles to nearly the speed of light, contributing to the population of cosmic rays that pervade our galaxy. And the mergers of neutron stars are thought to be the primary sites for the formation of many of the heaviest elements in the periodic table, including gold, platinum, and uranium. So the next time you look at a gold ring or other precious metal jewelry, consider this. The atoms that make up that jewelry were likely forged in the violent merger of two neutron stars, billions of years ago and billions of light years away. These extreme stars are not just distant curiosities, they're part of our cosmic heritage. As our journey through the strangest stars in the cosmos continues, we'll encounter even more exotic possibilities. What happens when neutron stars continue to accrete matter and exceed the maximum mass that can be supported by neutron degeneracy pressure? They collapse further to form black holes, objects so dense that not even light can escape their gravity. But there might be an intermediate stage, objects called quark stars, composed entirely of quark matter. These theoretical stars, which we'll explore in our next segment, would be even stranger than neutron stars. They would be slightly smaller and denser, and their properties would be governed by the strong nuclear force rather than gravity. Some astronomers believe that many objects we currently classify as neutron stars might actually be quark stars, or might have quark matter cores surrounded by shells of conventional neutron star material. The boundary between neutron stars and black holes is a fascinating frontier of astrophysics. Objects near this boundary challenge our understanding of matter at the highest densities and gravity at its most extreme. They invite us to explore the limits of our physical theories and to imagine states of matter unlike anything we can create on Earth. In our exploration of neutron stars, we've peered into a realm of extremes: extreme density, extreme gravity, extreme rotation, extreme magnetism. We've seen how these properties combine to create phenomena that challenge our understanding of physics. And we've glimpsed the connections between these exotic objects and the elements that make up our bodies and our world. But our journey through the strangest stars in the cosmos is just beginning. Join us in our next segment as we venture into even stranger territory, exploring stars made of exotic forms of matter and stars that exist only in theory, at least for now. We'll continue to push the boundaries of our understanding, exploring the most extreme objects and phenomena in our universe. As we leave the realm of neutron stars behind, we carry with us a deeper appreciation for the extremes that nature can achieve. In a universe filled with wonders, these remnants of stellar catastrophes rank among the strangest objects known to science. They remind us that the cosmos is not just vaster, but also stranger than we can imagine. And they invite us to keep exploring, to keep questioning, and to keep marveling at the bizarre reality we call home. As we continue our journey through the strangest stars in the cosmos, we venture into increasingly speculative territory. We've explored neutron stars, objects so dense that a teaspoonful would weigh billions of tons on Earth. But what if there's something even more extreme? What if, under certain conditions, neutron stars themselves are not the final stage of stellar evolution before black holes? Enter the theoretical realm of quark stars, objects that might represent an intermediate stage between neutron stars and black holes. and which push our understanding of matter to its very limits. To understand quark stars, we first need to delve deeper into the fundamental structure of matter. Everything around us, the air we breathe, the water we drink, the ground beneath our feet, is made of atoms. Each atom consists of a nucleus surrounded by a cloud of electrons. The nucleus, in turn, contains protons and neutrons. But the story doesn't end there. In the 1960s, physicists proposed that protons and neutrons themselves are not fundamental particles, but are composed of even smaller entities called quarks. This theory, now well established through numerous experiments, tells us that each proton and neutron contains 3 quarks bound together by the strong nuclear force, mediated by particles called gluons. Quarks come in 6 types, or flavors: up, down, strange, charm, top, and bottom. Ordinary matter consists primarily of up and down quarks. A proton contains 2 up quarks and 1 down quark, while a neutron contains 1 up quark and 2 down quarks. The other quark flavors are typically seen only in high-energy environments, such as particle accelerators or the early universe shortly after the Big Bang. Under normal conditions, quarks are always found in combinations that result in particles with integer electric charges. They're bound so tightly that no experiment has ever observed an isolated quark. This phenomenon, known as quark confinement, is a fundamental aspect of the strong nuclear force. But theory suggests that under extreme conditions, such as those found in the cores of neutron stars, the boundaries between individual neutrons might break down. The neutrons would dissolve into their constituent quarks, creating a soup of up and down quarks in a state of matter called quark matter, or quark-gluon plasma. This brings us to the concept of quark stars. In the extreme environment at the center of a massive neutron star, where densities exceed several times the nuclear density, the pressure might become so great that neutrons can no longer exist as distinct particles. Instead, they would be crushed to the point where the quarks inside them are liberated, creating a state of matter where quarks move freely within the star. If enough of the neutron star converts to this state, we might call it a quark star, essentially a gigantic hadron composed primarily of up and down quarks, possibly with some strange quarks as well. Such an object would be even more compact than a neutron star, with a slightly smaller radius for the same mass. The transition from a neutron star to a quark star could happen in several ways. One possibility is that a neutron star gradually converts to a quark star from the inside out as it accretes matter and its central density increases. Another possibility is that the conversion happens abruptly when the neutron star reaches a critical mass or density, perhaps triggered by a starquake or some other perturbation. The existence of quark stars remains theoretical. We haven't definitively identified any yet, but there are several candidates that astronomers are studying closely. These are objects that appear too small or too dense to be conventional neutron stars, but not dense enough to be black holes. One such candidate is an object called RX J18556.5-3754, discovered in 2002. Initial measurements suggested it was too small to be a neutron star, leading some astronomers to propose it might be a quark star. However, subsequent observations have called these measurements into question, and the object's status remains uncertain. Another candidate is the central object in the supernova remnant Cassiopeia A. This object's temperature appears to be decreasing faster than models of conventional neutron stars predict, which could be consistent with it being a quark star with different thermal properties. But again, other explanations are possible, and the evidence isn't conclusive. The challenge in identifying quark stars lies in the difficulty of measuring the sizes of these distant, compact objects with sufficient precision to distinguish them from neutron stars. Both types of objects are typically only about 20 kilometers across and located thousands of light years away. At such distances, they appear as mere points of light even in our most powerful telescopes. Astronomers employ various indirect methods to estimate their sizes, such as analyzing their thermal emission or the way they eclipse binary companions. But these methods involve many assumptions and uncertainties, making definitive identifications challenging. Moreover, there's ongoing debate among theoretical physicists about whether quark stars can actually exist as stable objects. Some models suggest that once quark matter forms in a neutron star's core, it would rapidly convert the entire star to quark matter. Other models indicate that the conversion might stop at a certain point, resulting in a hybrid star with a quark matter core surrounded by a neutron matter shell. The properties of quark stars, if they exist, would be fascinating to study. They would be slightly smaller and denser than neutron stars of the same mass. Their surface would be smooth and virtually incompressible, with a sharp boundary between the quark matter and the surrounding vacuum. Unlike the gradual change in density from the surface to the center of a neutron star, a quark star would have a nearly uniform density throughout. The surface of a quark star would be unlike anything we can readily imagine. It wouldn't be a solid surface as we think of on Earth, but rather a boundary where the density of quark matter suddenly drops to nearly zero. This boundary would be incredibly rigid due to the strong nuclear force binding the quarks together. If you could somehow stand on this surface, ignoring the fact that you'd be instantly vaporized by the extreme temperature and crushed by the intense gravity, it would feel harder than any material on Earth. The temperature of a newly formed quark star would be incredibly high, billions of degrees. At such temperatures, the star would emit most of its energy as gamma rays and X-rays. Over time, it would cool, with its emissions shifting to lower frequencies. Detecting this cooling process and comparing it to theoretical models could be one way to identify quark stars. The magnetic field of a quark star might also differ from that of a neutron star. In a neutron star, the magnetic field is generated primarily by the movement of charged particles in its outer layers, but in a quark star, the entire object is composed of charged particles, quarks, that can generate a magnetic field. Some theories suggest quark stars might have unique magnetic field configurations that could produce distinctive observational signatures. But perhaps the most intriguing aspect of quark stars is the possibility that they might contain strange quarks, in addition to up and down quarks. Strange quarks are heavier than up and down quarks and aren't found in ordinary matter. But calculations suggest that at the extreme densities inside quark stars, converting some up and down quarks to strange quarks might be energetically favorable, leading to a state of matter called strange quark matter. This brings us to an even more exotic possibility: strange stars. These would be quark stars composed primarily of strange quark matter, with roughly equal numbers of up, down, and strange quarks. The properties of strange quark matter are still not fully understood, but some theories suggest it might be the true ground state of matter at high densities, meaning it could be more stable than neutron matter, or even normal atomic nuclei under certain conditions. If strange quark matter is indeed the ground state of matter at high densities, it raises a fascinating possibility known as the strange matter hypothesis. This hypothesis suggests that once a small amount of strange quark matter forms, it could catalyze the conversion of ordinary matter that comes into contact with it, gradually transforming it into strange quark matter as well. This process has been likened to a phase transition, similar to how a small seed crystal can catalyze the crystallization of an entire solution. The strange matter hypothesis has led to some dramatic scenarios in science fiction and popular science, with visions of strangelet contamination, converting entire stars or even planets into strange matter. But fear not, the vast majority of physicists consider such scenarios extremely unlikely. For one thing, tiny amounts of strange matter, if they exist, would be electrically positive and would repel normal matter, preventing contact. And even if contact occurred, the conversion would likely require such extreme conditions of temperature and pressure that it couldn't propagate in normal environments. Rather than being a doomsday scenario, the strange matter hypothesis actually opens up intriguing possibilities for the nature of some astronomical objects. If strange quark matter is stable, then some or even all neutron stars might actually be strange stars. They might have thin crusts of normal matter, but their interiors would be composed of this exotic form of matter. The existence of strange stars would have profound implications for our understanding of matter and the forces that govern it. It would mean that what we consider normal matter isn't actually the most stable form of matter under all conditions. It would provide a natural laboratory for studying the strong nuclear force in regimes we can't access in terrestrial experiments. And it would add another fascinating chapter to the story of stellar evolution. But how might we distinguish strange stars from conventional neutron stars, or even regular quark stars composed primarily of up and down quarks? One possibility is through their cooling behavior. Strange stars would cool differently than neutron stars due to their different composition and thermal properties. Another is through the gravitational waves emitted when two compact objects merge. The distinctive properties of strange matter might leave a unique signature in these gravitational waves. The exploration of quark stars and strange stars connects to broader questions about the nature of matter under extreme conditions. In the early universe, shortly after the Big Bang, temperatures and densities were so high that all matter existed as a quark-gluon plasma. By studying quark stars, we're essentially studying a state of matter that dominated the universe during its earliest moments. This connection extends to modern experiments as well. Particle accelerators like the Large Hadron Collider can create tiny, short-lived droplets of quark-gluon plasma by colliding heavy atomic nuclei at nearly the speed of light. These experiments give us glimpses into the properties of quark matter, but they can't sustain the extreme densities thought to exist in quark stars. Astronomical observations of quark stars, if we can identify them, would complement these laboratory experiments, providing insights into the behavior of quark matter under conditions we can't recreate on Earth. The study of quark stars also has implications for our understanding of the maximum mass of neutron stars. Observations suggest there's an upper limit to how massive a neutron star can be, around 2 to 3 times the mass of our Sun. Beyond this limit, the neutron star would collapse into a black hole. But if quark stars exist, they might be able to support slightly more mass than neutron stars before collapsing, potentially explaining observations of unusually massive compact objects. As our observational capabilities improve, we may eventually be able to conclusively identify quark stars or strange stars. The next generation of gravitational wave detectors will be more sensitive to the mergers of compact objects, potentially allowing us to distinguish neutron stars from quark stars through their gravitational wave signatures. Advanced X-ray telescopes will provide more precise measurements of the sizes and thermal properties of compact objects, offering another avenue for identification. But even in the absence of definitive observations, the theoretical exploration of quark stars and strange stars enriches our understanding of the cosmos. It reminds us that the universe is not just vaster, but also stranger than we can imagine. It pushes the boundaries of our theories and invites us to consider possibilities beyond the familiar. The concept of quark stars represents a frontier where nuclear physics, particle physics, and astrophysics converge. It challenges us to extend our understanding of the fundamental forces and particles that make up our universe. And it highlights how the cosmos provides natural laboratories for testing physical theories under conditions we can never hope to recreate on Earth. In essence, to study these exotic stars is to study the intersection of the very large and the very small, the intersection of general relativity and quantum physics. It's here, at the frontiers of our knowledge, that we're most likely to discover new physics and gain new insights into the nature of reality. As we've seen, the transition from neutron stars to quark stars represents a fascinating possibility in stellar evolution. These theoretical objects, if they exist, would be among the densest objects in the universe, surpassed only by black holes. They would provide a window into the behavior of matter under conditions of extreme density and pressure. And they would remind us once again of the incredible diversity of objects that can exist in our universe. But quark stars aren't the only theoretical stellar objects that stretch the boundaries of our understanding. In our next segment, we'll explore even more speculative possibilities: stars made of dark matter, stars sustained by exotic particles, and stars that might exist in the distant future of our universe. We'll continue our journey through the strangest stars in the cosmos, venturing ever further into the realm where theory and observation meet, where the familiar gives way to the extraordinary, and where our cosmic imagination is pushed to its limits. Before we leave the realm of quark stars, it's worth noting the broader context in which these exotic objects exist. They represent one possibility in the rich tapestry of compact objects that can result from stellar evolution. From white dwarfs, sustained by electron degeneracy pressure, to neutron stars, sustained by neutron degeneracy pressure, to quark stars, sustained by the strong nuclear force between quarks, to black holes, where gravity overwhelms all known forces. Each represents a different outcome for stars of different masses. This progression illustrates a fundamental pattern in nature. As we probe more extreme conditions, new physics emerges, and familiar principles break down. The study of these extraordinary objects is not just a cataloguing of cosmic curiosities, it's a systematic exploration of the fundamental laws of physics pushed to their limits. And it's in these extreme regimes that we often find the clues that lead to revolutionary scientific advances. So as we bid farewell to quark stars and strange matter, we carry with us a deeper appreciation for the complexity and diversity of stellar objects. We've seen how stars, even in death, can take on forms so extreme and exotic that they challenge our understanding of matter itself. And we've glimpsed the profound connections between the stars above us and the fundamental particles that make up our world. Our journey continues, but we've already seen enough to appreciate the truth of the saying that the universe is not only stranger than we imagine, but stranger than we can imagine. Yet through science, we continue to push the boundaries of the imaginable, revealing a cosmos more wondrous than even our wildest dreams. We've journeyed from the familiar territory of conventional stars through the extreme realm of neutron stars and into the theoretical domain of quark stars. But our exploration of the strangest stars in the cosmos doesn't end there. Now, we venture even further into speculative territory, examining stellar objects that exist primarily in the equations of theoretical physicists and the imaginations of cosmologists. These hypothetical stars push the boundaries of known physics and challenge our understanding of what's possible in our universe. Let's begin with strange matter stars, which we touched on in our discussion of quark stars. These objects would be composed primarily of strange quark matter, a form of quark matter containing roughly equal numbers of up, down, and strange quarks. The strange quark is heavier than the up and down quarks found in ordinary matter and is typically created only in high-energy particle collisions. The fascinating thing about strange quark matter is that some theoretical calculations suggest it might be more stable than ordinary nuclear matter under certain conditions. If this is true, it raises the possibility that what we call neutron stars might actually be strange matter stars with thin crusts of conventional matter. But how would such objects form? One possibility is through the gradual conversion of neutron stars. If a small amount of strange quark matter forms in the core of a neutron star, perhaps through the extreme pressure converting some up and down quarks to strange quarks, it could catalyze the conversion of surrounding neutron matter. Over time, this process might transform much or all of the neutron star into strange quark matter. Another possibility is that strange matter might form during the supernova explosion that creates the neutron star. The extreme conditions during the collapse and bounce of the stellar core could produce small amounts of strange quark matter that then grow as the neutron star cools. The properties of strange matter stars would be even more extreme than those of conventional neutron stars, or quark stars composed primarily of up and down quarks. They would be slightly more compact, with different cooling properties, different crustal structures, and possibly different maximum masses before collapsing to black holes. Observationally, distinguishing strange matter stars from conventional neutron stars is challenging. Both would appear as small, dense objects with strong magnetic fields. But there might be subtle differences in their cooling behaviors, their mass-radius relationships, or the gravitational waves they emit when involved in mergers. Future observations with more sensitive instruments might be able to detect these differences and determine whether strange matter stars actually exist. But strange matter stars aren't the only hypothetical stellar objects that might exist. Another fascinating possibility is the existence of boson stars, objects composed not of fermionic matter like protons, neutrons, and electrons, but of bosonic matter, such as scalar fields. In particle physics, elementary particles are divided into two categories based on their intrinsic angular momentum, or spin. Fermions, like electrons, protons, and neutrons, have half-integer spin and obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state. This principle is responsible for the structure of atoms and the stability of white dwarfs and neutron stars against gravitational collapse. Bosons, on the other hand, have integer spin and can occupy the same quantum state, leading to phenomena like lasers and Bose-Einstein condensates. Familiar bosons include photons, particles of light, and gluons, carriers of the strong nuclear force. Less familiar are scalar bosons, like the Higgs boson, which have zero spin. Boson stars would be composed of scalar bosons bound together by gravity. Unlike fermions, bosons aren't subject to the Pauli exclusion principle. So what prevents a boson star from immediately collapsing under its own gravity? The answer lies in the Heisenberg uncertainty principle, which creates a quantum pressure that can balance gravity, similar to how electron or neutron degeneracy pressure supports white dwarfs and neutron stars. The properties of boson stars would depend on the specific scalar field that composes them. Some models predict that they could be very diffuse, with radii of thousands or even millions of kilometers. Others suggest they could be quite compact, similar in size to neutron stars. Some could be stable over long periods, while others might be prone to collapse into black holes. Observationally, detecting boson stars would be challenging because they wouldn't emit light directly. However, they would have gravitational effects on their surroundings. They could bend light from background sources through gravitational lensing, they could affect the orbits of nearby objects, and they might emit distinctive gravitational waves when they merge with other compact objects. Interestingly, boson stars have been proposed as alternatives to black holes in some scenarios. While they would appear similar to black holes in many respects, both being massive, compact, and dark, they have fundamental differences. Unlike black holes, boson stars don't have event horizons or singularities. Light and matter can, in principle, pass through them, though they might be scattered or absorbed in the process. Some researchers have even suggested that what we interpret as supermassive black holes at the centers of galaxies might actually be boson stars. While this is highly speculative, precision observations of the environments around these objects, particularly the Event Horizon Telescope's observations of the shadow around the supermassive object at the center of Galaxy Saturn Mate 7, are beginning to constrain such possibilities. Another category of hypothetical stars involves objects composed of exotic forms of dark matter. Dark matter, which makes up about 85% of the matter in the universe, doesn't interact with light or ordinary matter except through gravity. Its exact nature remains one of the biggest mysteries in modern physics. If dark matter consists of particles that can lose energy through some interaction, for example, by emitting dark photons, then these particles could, in principle, collapse to form dark matter stars. These objects would be invisible to conventional telescopes, but would have gravitational effects on their surroundings. Depending on the properties of the dark matter particles, dark matter stars could take various forms. They might be diffuse and extended, or compact and dense. They might be stable over long periods, or they might evolve and change over time. Because we know so little about the nature of dark matter, the possibilities are quite broad. Observationally, detecting dark matter stars would be even more challenging than detecting boson stars. Their primary effect would be gravitational, potentially causing lensing of background light sources or affecting the orbits of nearby objects. Some models suggest they might emit gamma rays or other high-energy radiation if ordinary matter falls onto them, providing another possible avenue for detection. The existence of dark matter stars would have profound implications for our understanding of cosmology. They could act as seeds for galaxy formation. They could influence the distribution of dark matter in galaxies, and they might even explain some of the anomalous gravitational lensing observations that have puzzled astronomers. Moving to even more speculative territory, let's consider Planck stars, theoretical objects proposed as alternatives to the singularities at the centers of black holes. According to classical general relativity, when a massive star collapses to form a black hole, the matter continues to collapse under its own gravity until it forms a singularity, a point of infinite density where the laws of physics as we understand them break down. However, many physicists are uncomfortable with the concept of singularities, viewing them as indications that our theories are incomplete rather than as real physical objects. Various approaches to quantum gravity, attempts to reconcile general relativity with quantum mechanics, suggest that there might be alternatives to singularities. One such alternative is the Planck star, named after Max Planck, one of the founders of quantum theory. A Planck star would form when matter collapsing in a black hole reaches a density where quantum gravitational effects become significant, halting the collapse and forming a compact object with a radius on the order of the Planck length, an incredibly tiny scale around 10 to the negative 35 meters. From the outside, a black hole containing a Planck star would look identical to a conventional black hole. It would have an event horizon, it would bend light and affect the orbits of nearby objects, and it would emit Hawking radiation, the quantum mechanical process by which black holes are theorized to slowly lose mass. But on the inside, the story would be very different. Instead of a singularity, there would be a Planck star, a stable, extremely dense object where quantum gravitational effects prevent further collapse. This star would contain all the information that fell into the black hole, potentially resolving the infamous black hole information paradox that has troubled physicists for decades. The existence of Planck stars would have implications for the ultimate fate of black holes. As a black hole emits Hawking radiation, it gradually loses mass. In conventional theory, this process continues until the black hole evaporates completely. But if the black hole contains a Planck star, the evaporation process might end differently. When the black hole shrinks to a size comparable to the Planck star inside it, some theories suggest that the event horizon might disappear, revealing the Planck star and releasing all the information that had been stored inside. Given that Planck stars would be hidden behind event horizons for most of their existence, observing them directly would be virtually impossible. However, if the scenario described above is correct, and Planck stars can be revealed as black holes evaporate, there might be observable consequences. The final stages of black hole evaporation would be marked by a burst of energy as the Planck star is exposed, potentially detectable as high-energy cosmic rays or gamma-ray bursts. Venturing even further into speculative territory, some theoretical physicists have proposed the existence of exotic compact objects that mimic the gravitational properties of black holes but have different internal structures. These include gravastars, gravitational vacuum stars, where a thin shell of matter surrounds a core of negative vacuum energy, fuzzballs, string theory objects where the event horizon is replaced by a quantum fuzz of strings, and black stars, objects where matter is compressed to just above its Schwarzschild radius, but prevented from further collapse by radiation pressure. Each of these proposals represents an attempt to reconcile the observed properties of black holes with different theoretical frameworks, particularly those that attempt to incorporate quantum mechanics. While these objects remain theoretical, Advances in gravitational wave astronomy and very long baseline interferometry, like the Event Horizon Telescope, are beginning to test some of their predictions against observations of candidate black holes. Another category of hypothetical stars involves objects that might exist in the very distant future of our universe. As the universe ages and cools, new types of structures may become possible. Physicist Freeman Dyson has speculated that in the far future, around 10 to the power of 37 years from now, when conventional stars have long since burned out, new types of stars might form through quantum fluctuations in the vacuum. These quantum stars would be very different from the stars we observe today. They would be much cooler, much less energetic, and would operate on timescales far longer than the current age of the universe. Their physics would be dominated by quantum mechanical processes rather than nuclear fusion. Even further in the future, around 10 to the power of 100 years from now, matter as we know it may cease to exist, with all particles having decayed through various processes. At this stage, black holes would dominate the universe, but even they would eventually evaporate through Hawking radiation, leading to a universe filled with only photons, neutrinos, and possibly other stable particles. In such a universe, gravitational attractions might still cause these particles to cluster over enormous timescales, forming what some have called photon stars or neutrino stars. Extremely diffuse objects held together by their minuscule gravitational attraction. The physics of such objects would be very different from anything we observe today, operating at energy scales and timescales that are almost unimaginable. While these far future hypothetical stars may seem like pure speculation, they represent serious attempts by physicists to extrapolate the known laws of physics to their ultimate conclusions. They remind us that the universe we observe today is just a snapshot in an ongoing cosmic story, and that the future may hold structures and phenomena as different from our current universe as our universe is from the primordial soup of the early Big Bang. Closer to home, and perhaps more testable, are models involving modifications of general relativity. Einstein's theory of general relativity has been remarkably successful in describing gravity in a wide range of contexts, from the solar system to binary pulsars to the large-scale structure of the universe. But there are reasons to believe it may not be the final word on gravity. For one thing, general relativity predicts singularities in black holes and at the Big Bang, which many physicists view as indications that the theory breaks down under extreme conditions. For another, general relativity has proven difficult to reconcile with quantum mechanics, suggesting that a more fundamental theory, a quantum theory of gravity, might be needed. Various modified theories of gravity have been proposed, including FR gravity, where the Einstein-Hilbert action is replaced by a function of the Ricci scalar, Brans-Dicke theory, where gravity is mediated by both the metric tensor and a scalar field, a massive gravity, where the graviton, the hypothetical particle that mediates gravity, has a non-zero mass. These modified theories of gravity can predict the existence of stars with properties quite different from those expected in general relativity. For example, some theories predict that neutron stars could be less compact, with larger radii for a given mass. Others suggest that the maximum mass of neutron stars could be different, or that their gravitational fields could deviate from the predictions of general relativity, particularly in the strong field regime. Observational tests of these predictions are becoming increasingly precise. Measurements of the masses and radii of neutron stars, observations of gravitational waves from neutron star mergers, and studies of phenomena like the Shapiro delay, the slowing of light as it passes through a gravitational field, are all providing constraints on modified theories of gravity and the properties of compact objects within these theories. As we've journeyed through the realm of hypothetical stars, we've ventured far from observational certainty into the domain of theoretical speculation. But this is how science progresses, by pushing the boundaries of what we know, by considering what might be possible, and by developing tests to distinguish between different possibilities. The study of hypothetical stars connects to some of the deepest questions in modern physics. What is the nature of matter under extreme conditions? How does gravity behave in the strong field regime? How can we reconcile general relativity and quantum mechanics? What is dark matter? What is the ultimate fate of our universe? These questions drive theoretical research and motivate the development of new observational techniques and instruments. From gravitational wave observatories like LIGO and Virgo, to X-ray telescopes like Chandra and XMM Newton, to radio interferometers like the Event Horizon Telescope, to proposed future missions like LISA, a space-based gravitational wave detector, astronomers and physicists are constantly devising new ways to probe the cosmos and test our theories. Some of the hypothetical stars we've discussed may never be observed directly. Others may be ruled out by future observations or refined theoretical calculations. Still others may join the pantheon of confirmed astronomical objects, as pulsars and black holes did in the 20th century. What's certain is that our exploration of the cosmos will continue to surprise and inspire us, revealing a universe more complex and more fascinating than we can imagine. As we conclude our journey through hypothetical stars, we're reminded of the words attributed to the astronomer Arthur Eddington. Not only is the universe stranger than we imagine, it is stranger than we can imagine. The theoretical possibilities we've explored represent our best attempts to push the boundaries of the imaginable, to envision forms of matter and gravity beyond our current understanding. In our next segment, we'll return to somewhat firmer observational ground, exploring Thorne-Zhitkov objects, theoretical stars within stars that, while still speculative, have more direct connections to observed phenomena. These bizarre stellar hybrids, where a neutron star resides inside a red supergiant, represent another frontier in our understanding of stellar evolution and the strange configurations that stars can adopt. So join us as we continue our journey through the strangest stars in the cosmos, where each new object we encounter challenges our understanding and expands our cosmic imagination. The universe is vast and ancient, and it has had ample time and space to explore possibilities that stretch the limits of our theories and observations. By studying these extreme and exotic objects, we gain insights not just into the cosmos, but into the fundamental laws that govern all of reality. Our journey through the strangest stars in the cosmos has taken us from the extreme density of neutron stars to the theoretical realms of quark stars and various hypothetical stellar objects. Now, we turn our attention to a bizarre stellar hybrid that combines aspects of both ordinary stars and compact stellar remnants, the Thorne-Zhitkov object, or TZO for short. Imagine a star within a star, a neutron star residing at the center of a red supergiant, like a cosmic version of a Russian nesting doll. This is the basic concept of a Thorne-Zhitkov object, named after the physicists Kip Thorne and Anna Zhitkov, who first proposed their existence in 1977. These objects represent one of the strangest possible configurations of stellar matter and challenge our understanding of stellar evolution. To understand how such a bizarre object might form, we need to consider the life cycles of binary star systems. Most stars in our galaxy aren't solitary like our Sun, but exist in binary or multiple star systems, where two or more stars orbit a common center of mass. When these stars are massive, their evolution can lead to some truly exotic outcomes. Picture a binary system consisting of two massive stars. The more massive star will evolve faster, eventually exhausting its nuclear fuel and exploding as a supernova, leaving behind a neutron star. If this explosion doesn't disrupt the binary system, the neutron star will continue orbiting its companion. As the companion star evolves, it will eventually expand into a red giant or supergiant phase. If the orbital separation is small enough, the neutron star may be engulfed by the expanding outer layers of its companion. Once inside, the neutron star begins to spiral toward the core of the giant star due to frictional drag. Under normal circumstances, this spiraling would continue until the neutron star merges with the core of the giant star. But in the case of a Thorne-Zhitkov object, something different happens. The neutron star reaches the center of the giant star, but doesn't merge with its core in the conventional sense. Instead, it replaces the core, with the neutron star essentially becoming the new engine at the heart of the giant star. The result is a hybrid object with the outward appearance of a red supergiant, a huge cool star with a diameter that could extend beyond the orbit of Mars or even Jupiter if placed at the center of our solar system. But at its center, instead of a conventional stellar core fusing hydrogen or helium, there's a neutron star, an object so dense that a teaspoonful would weigh billions of tons on Earth. The interior structure of a Thorne-Jitkov object would be like nothing else in the universe. Surrounding the central neutron star would be a zone where matter is gradually accreting onto the neutron star's surface. This accretion process would release enormous amounts of energy, primarily in the form of neutrinos. Further out, there would be a convective envelope of normal stellar material, primarily hydrogen and helium, with some heavier elements. This envelope would be quite similar to the outer layers of a conventional red supergiant. To an observer with a telescope, a Thorne-Jitkov object would probably look much like any other red supergiant star, making them difficult to identify through casual observation. But the nuclear processes occurring within a Thorne-Jitkov object would be quite different from those in a normal star. In a conventional star, nuclear fusion occurs when atomic nuclei are driven together by the extreme pressure and temperature at the star's core, overcoming their electrostatic repulsion. The fusion process typically begins with hydrogen fusing into helium, then proceeds through a series of stages where increasingly heavy elements are formed. In a Thorne-Jitkov object, however, the extreme conditions near the neutron star can support more exotic nuclear processes. One of these is the rapid proton capture process, or RP process, where atomic nuclei rapidly accumulate protons, building heavier elements in sequences that aren't possible in normal stellar nucleosynthesis. This unusual nucleosynthesis could produce distinctive chemical signatures, particularly an overabundance of rare elements like lithium, rubidium, molybdenum, and yttrium. These elements would be carried to the star's surface by convective currents, potentially making them detectable in the star's spectrum. The existence of such a unique nuclear forge within a Thorne-Jitkov object makes these hypothetical stars particularly interesting from the perspective of galactic chemical evolution. If they exist in significant numbers, they could be important contributors to the production of certain rare elements in the universe. But do Thorne-Jitkov objects actually exist? Despite being theoretically possible, confirming their existence observationally has proven challenging. The problem is that they would look superficially similar to ordinary red supergiants, with the main distinguishing features being subtle differences in their chemical compositions that require detailed spectroscopic analysis to detect. In 2014, a team of astronomers led by Emily Levesque announced a promising candidate for a Thorne-Jitkov object. The star, designated HV2112 in the Small Magellanic Cloud, a satellite galaxy of our Milky Way, showed the enhanced abundances of specific elements expected in a Thorne-Jitkov object. It had been previously classified as a red supergiant, but stood out due to its unusual spectral features. However, subsequent analysis has cast some doubt on this identification. Alternative explanations for the star's unusual chemical signature have been proposed, including the possibility that it's a normal red supergiant that has experienced an unusual nucleosynthetic history. The debate continues, and astronomers are still searching for definitive evidence of Thorne-Jitkov objects. One of the challenges in identifying these objects is their expected rarity, the specific sequence of events required to form a Thorne-Jitkov object, a supernova that doesn't disrupt the binary system, followed by the engulfment of the neutron star by its companion, followed by the spiraling of the neutron star to the center without disrupting the giant star, is quite uncommon. Models suggest that there might be only a few dozen Thorne-Jitkov objects in a galaxy the size of the Milky Way at any given time. Another challenge is their expected lifetime. Once formed, a Thorne-Jitkov object might be stable for only about 10,000 to 100,000 years, a mere blink of an eye in cosmic terms. This short lifetime makes them even harder to catch in the act, so to speak. Despite these challenges, the search for Thorne-Zhitkov objects continues. Large spectroscopic surveys of red supergiants, especially those with unusual properties, may eventually turn up more candidates. Advances in astronomical techniques and instrumentation are making it possible to detect ever more subtle features in stellar spectra, potentially allowing astronomers to distinguish Thorne-Zhitkov objects from normal red supergiants with greater confidence. If confirmed, the existence of Thorne-Zhitkov objects would have profound implications for our understanding of stellar evolution, binary star systems, and the nuclear processes that produce the elements in our universe. These bizarre stellar hybrids would represent a previously unknown evolutionary pathway for massive stars, and would demonstrate that stars can exist in configurations more exotic than previously imagined. The fate of a Thorne-Zhitkov object is another fascinating aspect of these hypothetical stars. Eventually, the neutron star at the center would accrete enough material to exceed the maximum mass that can be supported by neutron degeneracy pressure, about 2 to 3 times the mass of our Sun, depending on the neutron star's rotation and internal composition. At this point, the neutron star would collapse into a black hole. The newly formed black hole would then rapidly accrete the surrounding stellar material, potentially leading to the formation of a gamma-ray burst, one of the most energetic explosions known in the universe. Alternatively, the entire star might collapse directly into a black hole without a dramatic explosion, or the outer layers might be ejected while the core collapses. The details of this final fate depend on various factors, including the mass of the original neutron star, the mass of the supergiant envelope, and the rotation of the system. Different models predict different outcomes, and without confirmed observations of Thorne-Zhitkov objects, it's difficult to constrain these models. One intriguing possibility is that Thorne-Zhitkov objects might be related to certain types of gamma-ray bursts, brief, intense flashes of gamma rays that are among the most energetic phenomena in the universe. If the collapse of a Thorne-Zhitkov object can indeed trigger a gamma-ray burst, then some of the bursts we observe might be the final farewell of these bizarre stellar hybrids. Another possibility is that Thorne-Zhitkov objects might be connected to certain types of unusual supernovae. In recent years, astronomers have discovered supernovae with properties that don't fit neatly into the standard classification scheme. Some of these might be the explosive deaths of stars with unusual compositions or structures, potentially including Thorne-Zhitkov objects. The study of Thorne-Zhitkov objects also connects to broader questions about the interactions between compact objects and normal stars. Similar processes to those involved in the formation of Thorne-Zhitkov objects may occur in other contexts, such as when black holes or neutron stars accrete material from companion stars in X-ray binary systems, or when compact objects spiral into the atmospheres of giant stars in common envelope events. Understanding these interactions is crucial for many areas of astrophysics, from the formation of gravitational wave sources to the production of heavy elements through processes like the R process, rapid neutron capture. Thorne-Zhitkov objects represent an extreme case of such interactions, where the compact object actually takes up residence at the center of its companion star. The concept of a star within a star also highlights the incredible diversity of structures that can exist in our universe. Stars are not simply homogeneous balls of gas, but can have complex internal structures, sometimes including other stellar remnants. This complexity reminds us that the boundaries between different types of astronomical objects are not always clear-cut, and that nature can create hybrid objects that challenge our categorical thinking. It's worth noting that Thorne-Zhitkov objects were first proposed by Kip Thorne, one of the world's leading experts on black holes and general relativity, and Anna Zhitkov, an astrophysicist with expertise in stellar evolution. Thorne later became famous for his work on gravitational waves and his role as scientific consultant for the movie Interstellar. The concept of Thorne-Zhitkov objects demonstrates how theoretical physics can predict the existence of objects that aren't immediately obvious from observations, guiding astronomers in their search for new phenomena. The continuing search for Thorne-Zhitkov objects exemplifies the interplay between theory and observation that drives progress in astrophysics. Theorists propose the existence of objects based on our best understanding of physical laws, and observers then search for evidence of these objects, sometimes finding them, sometimes not finding them, and sometimes finding something unexpected that leads to new theoretical developments. This cycle of prediction, observation, and refinement has led to many of the most important discoveries in astronomy, from the prediction and subsequent discovery of Neptune, based on irregularities in Uranus's orbit, to the prediction and later confirmation of gravitational waves, based on Einstein's theory of general relativity. Thorne-Zhitkoff objects represent a prediction still awaiting definitive confirmation, a potential discovery that would add another chapter to this ongoing story of scientific progress. As we continue our journey through the strangest stars in the cosmos, we're reminded of the incredible diversity of objects that can exist within our universe. From conventional stars like our Sun, to the ultra-dense neutron stars, to the theoretical quark stars, to the star within a star configuration of Thorne-Zhitkoff objects. The cosmos continually surprises us with its creativity. Each type of stellar object we've discussed represents a different set of physical conditions, a different balance of forces, a different stage in the cosmic recycling of matter and energy. Together, they form a rich tapestry of phenomena that challenges our understanding and expands our appreciation of the universe's complexity. In our next segment, we'll explore another extreme type of star, hypergiants, the most massive and luminous stars known. These stellar behemoths push the limits of stellar mass and brightness, living brief but spectacular lives before dying in catastrophic supernova explosions. Their enormous influence on their surroundings and their crucial role in enriching the universe with heavy elements make them some of the most important stars in cosmic history. So join us as we continue our journey through the strangest stars in the cosmos, venturing from the theoretical realm of stars within stars to the observational reality of stellar giants that dwarf our Sun in every respect. The universe is vast and varied, and the diversity of stars it contains reflects the boundless creativity of nature operating through the laws of physics. Each new type of star we encounter adds another piece to the cosmic puzzle, bringing us closer to a comprehensive understanding of our stunning universe. Before we leave the realm of Thorne-Zhitkoff objects, it's worth reflecting on what these hypothetical stars tell us about the nature of scientific inquiry. They remind us that the universe often realizes possibilities that seem bizarre or counterintuitive from our limited human perspective. A neutron star, itself an object of extreme density and exotic physics, residing inside another star is a concept that stretches the imagination. Yet the laws of physics not only allow for such a configuration, but suggest specific ways it might form and specific observational signatures it might produce. Science progresses by following the implications of our theories wherever they lead, even when they point to phenomena that seem strange or unlikely. And time and again, the universe has proven to be stranger than we imagined, harboring objects and phenomena that challenge our preconceptions. Thorne-Zhitkoff objects, if they exist, would be another example of this cosmic strangeness, another reminder of the unbounded creativity of nature operating through physical law. As we bid farewell to these bizarre stellar hybrids, we carry with us a deeper appreciation for the complexity of stellar evolution and the intricate dance of binary star systems. We've glimpsed a configuration of matter unlike anything else in the universe, a neutron star, already an object of extremes, serving as the core of a supergiant star, creating a hybrid object with properties of both. In our journey through the strangest stars in the cosmos, Thorne-Zhitkoff objects stand out as perhaps the most structurally bizarre, a true testament to the diversity of stellar phenomena that our universe can produce. Our cosmic journey has taken us through some of the densest and most exotic stars in the universe: neutron stars, theoretical quark stars, hypothetical exotic stars, and the bizarre stellar hybrids known as Thorne-Zhitkoff objects. Now, we turn our attention to stars that stand out not for their density or exotic composition, but for their sheer size and luminosity. The hypergiants, true monsters of the stellar world. Imagine a star so enormous that if placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, engulfing Mercury, Venus, Earth, Mars, and the asteroid belt. Imagine a star so luminous that it shines with the light of millions of suns, visible across vast intergalactic distances. These are the hypergiants, the most massive and luminous stars known to exist in our universe. Hypergiants represent the upper extremes of what's possible for a star. They push against the very limits of stellar mass and luminosity, teetering on the edge of stability. Their lives are brief but spectacular, and their deaths seed the cosmos with the heavy elements necessary for planets and life. They are cosmic engines of creation through destruction, and their influence extends far beyond their immediate surroundings. But what exactly makes a star a hypergiant? The classification is somewhat loose, but generally, hypergiants are stars with masses greater than about 30 times that of our Sun and luminosities millions of times greater. They typically have radii hundreds or even thousands of times larger than our Sun. These stars belong to the upper end of the stellar classification system, often carrying the luminosity class designation 0, written as 0 to distinguish them from mere supergiants, luminosity class I. The most massive hypergiants known have masses around 200 to 300 times that of our Sun, approaching what theorists believe is the upper limit for stellar mass. Beyond this limit, the outward pressure from the star's own radiation becomes so great that it overcomes gravity, preventing additional material from being incorporated into the star. The most luminous hypergiants shine with the light of several million suns. This extreme luminosity comes at a cost. These stars burn through their nuclear fuel at a prodigious rate, giving them lifespans of only a few million years, compared to the roughly 10 billion year lifespan of a star like our Sun. They live fast and die young, cosmic rock stars burning brightly for a brief moment in astronomical terms. One of the largest known hypergiants is VY Canis Majoris, a red hypergiant in the constellation Canis Major, about 3,300 light-years from Earth, with a radius estimated at between 1,400 and 2,100 times that of our Sun. VY Canis Majoris is one of the largest stars known. If placed at the center of our solar system, its surface would extend beyond the orbit of Saturn. Another notable hypergiant is UI Scuti, a red supergiant or hypergiant in the constellation Scutum, about 9,500 light-years away. Some measurements suggest it may be even larger than VY Canis Majoris, with a radius potentially up to 1,700 times that of our Sun, though such measurements have significant uncertainties. In terms of mass and luminosity,
time before anything
R136,
no
A1,
stars,
in the
no
Large
planets,
Magellanic
no
Cloud
light,
stands out,
no darkness,
with a mass
not even
estimated
space
at around
itself.
300 times
The
that of our
universe we
Sun,
know and live in
and a
today was once
luminosity
a blank
approximately
canvas,
5
so
million
empty
times
and
greater.
silent.
It represents
almost
one of
as
the
if
most
it wasn't there
extreme
at all.
stars known,
But then,
due to its
in a
tremendous
moment, we
mass,
can hardly fathom.
it's expected
Everything
to end its
changed.
life in a particularly
This is the story
energetic
of how our
supernova
universe came to
explosion,
life.
or possibly even
But
a
here's the
hypernova.
catch. It
An
didn't
even
come
more
from
powerful
somewhere.
stellar
It
explosion.
came from nothing.
The life cycle
A
of a
nothingness so
hypergiant is a
complete,
dramatic
so
story of
profound,
extremes.
that it defies
These
everything
stars
we think
begin
we
their
know about
lives
the laws
in
of
massive
reality.
molecular clouds.
How did it
where
happen?
gravity pulls together
What sparked
vast
the
amounts
birth
of gas and
everything
dust.
around us?
Due to their immense
This journey
mass,
begins in the
they
most
reach the
unimaginable
temperatures and
place.
pressures necessary for
A
nuclear
place where
fusion,
everything,
much more
even the
quickly
idea
than
of
smaller
beginning,
stars,
didn't even
skipping
exist.
the long, slow contraction phase that stars like our Sun experience. Once nuclear fusion
Imagine a
ignites in their
time before
cores,
anything existed.
hypergiants shine
No
with
stars,
incredible
no
brilliance.
planets,
Their
no light,
enormous
no
mass
darkness,
creates tremendous
not even
pressure
space
and temperature
itself.
at their cores,
The universe
driving
we know
nuclear
and live in
fusion at
today
a furious
was
pace.
once a blank canvas,
Unlike our Sun,
so
which
empty
fuses hydrogen
and
into
silent,
helium in a
it was
steady,
almost as if
controlled
it wasn't there
process
at
that will
all.
last billions
But
of
then,
years,
in a moment we can hardly
hypergiants
fathom,
burn through their nuclear
everything
fuel
changed.
in a cosmic
This
blink
is
of
the
an eye.
story of
how
The
our
internal
universe
structure of a
came to life.
hypergiant is
But
also
here's
more
the
complex
catch.
than that
It
of
didn't come
smaller
from
stars.
somewhere.
While a
It came
star,
from nothing.
like our Sun,
A
has a
nothingness so
relatively
complete,
simple structure,
so profound,
a core where
that it
nuclear fusion
defies
occurs,
everything we think
surrounded
we
by
know about the
radiative and
laws
convective
of
zones.
reality. How
Hypergiants
did
can
it
have
happen?
multiple shells where
What
different
sparked
nuclear
the birth
fusion
of
processes
everything
occur
around us?
simultaneously.
This journey begins
At their
in the
cores,
most
they may have
unimaginable
already
place,
exhausted their
a place
hydrogen
where
and
everything,
moved on to fusing
even the
helium
idea of
or
beginning,
even heavier elements,
didn't even
while their outer
exist.
layers still contain unprocessed hydrogen. This layered structure creates a sort of stellar onion, with each layer corresponding to a different stage of nuclear fusion. At the center, the star might be fusing silicon into iron, while in successive outer layers, it fuses oxygen, neon, carbon, helium, and finally, in the outermost layer, hydrogen. This progression represents the star burning through its nuclear fuel, moving to increasingly heavier elements as lighter ones are exhausted. But the most distinctive feature of hypergiants is their instability. These stars exist near what astronomers call the Eddington limit, the point at which the outward pressure from a star's radiation balances the inward pull of gravity. Beyond this limit, the star would blow itself apart. Hypergiants tread dangerously close to this limit, experiencing tremendous mass loss as their outer layers are driven off by their own intense radiation. This mass loss can be spectacular. Hypergiants like Eta Carinae eject massive shells of material in dramatic outbursts, temporarily increasing their brightness by factors of tens or even hundreds. These outbursts can be so bright that the star becomes one of the brightest in the night sky, visible even in daylight, despite being thousands of light years away. Eta Carinae, located about 7,500 light-years from Earth in the constellation Carina, provides a particularly dramatic example of hypergiant instability. In the 1840s, it underwent a massive eruption known as the Great Eruption, becoming the second brightest star in the night sky, despite its great distance. During this event, it ejected an amount of material equivalent to at least 10 times the mass of our Sun, creating the spectacular bipolar nebula that now surrounds it, known as the Homunculus Nebula. This nebula continues to expand at speeds of around 650 kilometers per second and contains a remarkable amount of dust, about 20 Earth masses worth. The dust absorbs much of Eta Carinae's visible light, re-radiating it as infrared, making Eta Carinae one of the brightest infrared sources in the sky. Today, Eta Carinae appears to be a binary system, with a primary star that's a luminous blue variable hypergiant with a mass around 100 of the Sun, known as luminous blue variables, undergo periodic eruptions and dramatic changes in appearance. Others, like yellow hypergiants, experience phases of rapid expansion and contraction as they struggle to maintain equilibrium. This instability is intrinsically linked to the evolutionary stage of these massive stars. As they exhaust the hydrogen in their cores and begin fusing heavier elements, they enter a phase of their lives where they become increasingly unstable. Their outer layers expand and contract, their brightness fluctuates, and they eject shells of material in violent outbursts. One particularly interesting class of hypergiants are the yellow hypergiants, stars that exist in a transitional stage as they evolve from being red supergiants to blue supergiants, or vice versa. These stars exist in what's known as the yellow evolutionary void on the Hertzsprung-Russell diagram, a plot that astronomers use to classify stars based on their temperature and luminosity. The yellow evolutionary void is a region where stars are highly unstable due to an unfortunate coincidence. The temperature range where helium begins to ionize in the star's atmosphere overlaps with the temperature where hydrogen becomes partially ionized. This creates a zone in the star's atmosphere with very high opacity, trapping energy and leading to violent instabilities. Stars like Rho Cassiopeiae, a yellow hypergiant about 10,000 light-years from Earth, occasionally undergo dramatic outbursts as they struggle to pass through this unstable region. In the year 2000, Rho Cassiopeiae experienced such an outburst, dropping in temperature from about 7,000 degrees Celsius to about 4,000 degrees in just a matter of months, and ejecting a shell of material with a mass equivalent to about 10,000 Earths. The fate of hypergiants is as dramatic as their lives. Due to their enormous mass, they're destined to end their lives in catastrophic supernova explosions. But unlike less massive stars, which typically explode as type Hoshū supernovae, the most massive hypergiants might explode as even more energetic events known as hypernovae. A hypernova is essentially a supernova on steroids, an explosion that can be tens or even hundreds of times more energetic than a regular supernova. These explosions are so powerful that they're thought to be the source of the longest and most powerful gamma-ray bursts, brief but incredibly intense flashes of high-energy radiation that can briefly outshine entire galaxies. During a hypernova explosion, the core of the star collapses directly into a black hole, while the outer layers are blown outward with enough energy to accelerate some material to a significant fraction of the speed of light. The collision between this ultra-fast material and the surrounding interstellar medium creates the gamma-ray burst. But not all hypergiants may end their lives in this way. Some theories suggest that the most massive stars might undergo a process called pair instability supernova. In this scenario, the core of the star becomes so hot that gamma rays within it begin to spontaneously convert into pairs of electrons and positrons, the antimatter equivalent of electrons. This conversion reduces the radiation pressure supporting the star against gravity, causing it to partially collapse. This collapse raises the core temperature even further, triggering an explosive burst of nuclear fusion that completely disrupts the star. No remnant is left behind. No neutron star, no black hole, just an expanding shell of stellar debris. These explosions would be among the most energetic events in the universe, briefly outshining entire galaxies. For slightly less massive hypergiants, another possibility is a pulsational pair instability supernova. In this case, the pair production causes a partial collapse that triggers an explosive burst of fusion, but not enough to completely disrupt the star. Instead, the star ejects a massive shell of material and then contracts. This process can repeat several times before the star finally collapses to form a black hole. The effects of hypergiant deaths extend far beyond the stars themselves. These catastrophic explosions scatter newly formed heavy elements across space, enriching the interstellar medium with the raw materials for new stars, planets, and eventually life. The shockwaves from the explosions can also trigger the collapse of nearby molecular clouds, catalyzing the formation of new stars. Indeed, the role of hypergiants in the cosmic ecosystem can't be overstated. Despite their rarity, they make up just a tiny fraction of all stars. They have a disproportionate impact on their surroundings and on the chemical evolution of galaxies. They're cosmic alchemists, forging heavy elements in their cores and scattering them across space when they die. The elements created in the cores of hypergiants and in their explosive deaths include many that are essential for life as we know it: carbon, nitrogen, oxygen, phosphorus, and many more. In a very real sense, we owe our existence to these stellar giants and their catastrophic death billions of years ago. But hypergiants aren't just important for their role in cosmic chemical evolution. They're also crucial for understanding the limits of stellar physics. How massive can a star be? How luminous? What processes define the upper boundaries of stellar mass and luminosity? By studying hypergiants, astronomers gain insights into these fundamental questions. Observing hypergiants presents unique challenges. Their extreme luminosity makes them visible across vast cosmic distances, but it also makes it difficult to study their details, as their brightness can overwhelm sensitive instruments. Additionally, many hypergiants are shrouded in dust, either ejected by the stars themselves or present in the dense star-forming regions where these massive stars are born. Modern telescopes operating at various wavelengths, from radio to gamma rays, are helping astronomers pierce these dusty veils and study hypergiants in unprecedented detail. Infrared telescopes, like the James Webb Space Telescope, which can see through dust, are particularly valuable for these studies. One of the most exciting prospects for future research is the possibility of observing a hypergiant explosion in real time. Given their short lifespans, at least a few hypergiants in our galaxy are likely to explode in the near astronomical future, perhaps in the next few thousand years, perhaps tomorrow. When one does, it will provide an unprecedented opportunity to study these cosmic catastrophes up close. In the meantime, astronomers continue to search for and study hypergiants throughout our galaxy and beyond. Each new discovery adds to our understanding of these cosmic behemoths and their role in the grand story of stellar evolution. As we leave the realm of hypergiants, we carry with us a deeper appreciation for the diversity of stellar objects and the extremes that stars can reach. From the ultra-dense neutron stars to the incomprehensibly massive hypergiants, the cosmos offers a stunning array of stellar phenomena that challenge our understanding and expand our cosmic perspective. In our next segment, we'll explore yet another fascinating category of unusual stars: variable stars. Objects whose brightness changes over time due to a wide variety of physical processes. From regular pulsators that expand and contract like cosmic heartbeats, to eruptive variables that undergo dramatic outbursts, to eclipsing binaries where stars dance around each other in cosmic ballets. The world of variable stars offers yet another dimension of stellar strangeness for us to explore. So join us as we continue our journey through the strangest stars in the cosmos, each type revealing different aspects of stellar physics and contributing to our ever-growing understanding of the universe and its wonders. The story of stars is, in many ways, the story of the universe itself, a tale of matter and energy, of creation and destruction, of cycles that span billions of years yet follow the unchanging laws of physics. As we bid farewell to the realm of hypergiants, we're reminded once again of the incredible diversity of stellar objects and the boundless creativity of nature operating through physical law. These stellar titans, though rare, play a crucial role in the cosmic ecosystem, forging heavy elements and scattering them across space, seeding the universe with the raw materials for planets and life. They remind us that in the cosmic story, even the most catastrophic endings can lead to new beginnings, as the debris from exploded hypergiants becomes the stuff of new stars, new worlds, and perhaps even new life. Our cosmic journey has taken us through some of the most extreme stellar objects in the universe, from the ultra-dense neutron stars to the mind-bogglingly massive hypergiants. Now, we turn our attention to stars that stand out not for their static properties, but for their dynamic behavior, variable stars. The cosmic flickerers, whose brightness changes over time. The night sky may appear unchanging to the casual observer, with stars maintaining their steady glow night after night. But astronomers know better. Many stars are not constant in their brightness, but vary over time, some in regular, predictable patterns, others in erratic, unpredictable ways. These are the variable stars, and they come in a bewildering variety of types, each telling us something different about stellar physics and evolution. At the most basic level, variable stars can be divided into two main categories: intrinsic variables, where the star itself changes in brightness due to physical processes within or on the star, and extrinsic variables, where the apparent brightness changes due to external factors like eclipses or rotation. Among the intrinsic variables, one of the most important classes is the pulsating variables, stars that physically expand and contract, becoming brighter and dimmer as they do so. These stellar pulsations are like cosmic heartbeats, and they come in many varieties, each with its own characteristic period, amplitude, and underlying physical mechanism. Perhaps the most famous pulsating variables are the Cepheid variables, named after the prototype star Delta Cephei. These are yellow supergiant stars that pulsate with remarkable regularity, completing a cycle of expansion and contraction in a period ranging from about 1 to 70 days. As they pulsate, their brightness can vary by as much as 2 magnitudes, a change in brightness by a factor of about 6. What makes Cepheid variables especially important is the direct relationship between their pulsation period and their intrinsic luminosity. The longer the period, the more luminous the star. This period luminosity relationship, discovered by Henrietta Swan Leavitt in 1908, provides astronomers with a powerful tool for measuring cosmic distances. Here's how it works. By observing a Cepheid variable and measuring its pulsation period, astronomers can determine its intrinsic luminosity. By comparing this intrinsic luminosity with the star's apparent brightness as seen from Earth, they can calculate how far away the star is. This technique has been crucial for establishing the cosmic distance scale and was instrumental in Edwin Hubble's discovery of the expansion of the universe in the 1920s. The physical mechanism behind Cepheid pulsations is a feedback process involving the ionization of helium in the star's atmosphere. When the star is compressed, the temperature and pressure increase, causing helium to become ionized. This ionization absorbs energy, making the stellar atmosphere more opaque and causing it to trap more heat. The increased heat creates pressure that pushes the outer layers outward, causing the star to expand. As the star expands, it cools, allowing the helium to recombine with electrons. This makes the atmosphere more transparent, allowing heat to escape. The loss of heat reduces the pressure, and gravity pulls the outer layers back inward, compressing the star again and starting the cycle anew. This mechanism, known as the Kappa mechanism, operates like a heat engine, converting thermal energy into mechanical energy. Another important class of pulsating variables is the RR Lyrae stars, named after the prototype star RR Lyrae. These are older, less massive stars than Cepheids, typically with about half the mass of our Sun. They pulsate with periods of less than a day, typically around 12 hours, and have brightness variations of about 1 magnitude, a change by a factor of about 2.5. Like Cepheids, RR Lyrae stars have a relationship between their pulsation periods and their intrinsic luminosities, though it's not as strong as the Cepheid relationship. Still, because all RR Lyrae stars have similar luminosities, they serve as standard candles for measuring distances. They're particularly useful for studying the structure of our Milky Way galaxy because they're common in globular clusters, dense collections of old stars that orbit the galactic center. The pulsation mechanism for RR Lyrae stars is similar to that of Cepheids, involving the Kappa mechanism operating in a layer of partially ionized hydrogen near the star's surface. The regularity of these pulsations makes RR Lyrae stars valuable cosmic clocks, ticking away with remarkable precision over billions of years. Moving to longer pulsation periods, we encounter the Mira variables, named after the prototype star Mira, also known as Omicron Ceti. These are red giant stars that pulsate with periods ranging from about 80 to 1,000 days. Their brightness variations are among the most dramatic of any variable stars, sometimes changing by more than 6 magnitudes, a factor of more than 250 in brightness. Mira itself is a striking example. At its brightest, it can be visible to the naked eye, but at its dimmest, it requires a telescope to see. This dramatic variation, coupled with its red color, made Mira a subject of wonder to ancient astronomers. Its name, which means wonderful or astonishing in Latin, reflects the awe it inspired. The pulsation mechanism for Mira variables is more complex than for Cepheids and RR Lyrae stars. It involves interactions between shockwaves propagating through the star's atmosphere and molecular formation processes. These long-period pulsations are less stable than those of Cepheids, with cycle-to-cycle variations in both period and amplitude. Beyond these well-known types, there's a zoo of other pulsating variables, including Delta Scuti stars, with periods of a few hours, Beta Cephei stars, with periods of a few hours to a day, and ZZ Ceti stars, which are pulsating white dwarfs with periods of just a few minutes. Each type represents a different stage of stellar evolution or a different mass range, and each provides unique insights into stellar interiors and physics. Moving from pulsating variables to more dramatic stellar behavior, we encounter the eruptive variables, stars that undergo sudden, often unpredictable increases in brightness due to violent processes on their surfaces or in their atmospheres. Perhaps the most spectacular eruptive variables are the novae. Despite their name, which means new in Latin, novae aren't new stars at all. They're binary systems consisting of a white dwarf, the dense remnant of a star like our Sun, and a main sequence or giant companion star. The white dwarf's strong gravity pulls hydrogen from its companion, accumulating it on the white dwarf's surface. As this hydrogen layer builds up, the pressure and temperature at its base increase until nuclear fusion ignites in a runaway process. This thermonuclear explosion blows off the accumulated hydrogen in a bright outburst that can increase the system's brightness by 10 to 15 magnitudes, a factor of 10,000 to 1 million in brightness. After the outburst, the cycle begins again, with the white dwarf accumulating more hydrogen from its companion. Some systems, known as recurrent novae, undergo outbursts every few decades. Others may have recurrence times of thousands or millions of years, making them appear as one-time events on human timescales. In either case, the white dwarf survives the explosion, distinguishing novae from the more catastrophic supernovae, where the star is completely destroyed. Even more dramatic than novae are supernovae, which we've touched on in previous segments. These are not truly variable stars in the usual sense, as the change in brightness is a one-time, catastrophic event rather than a recurring variation. However, they represent the most extreme changes in stellar brightness known, increasing by 20 magnitudes or more, a factor of 100 million in brightness. On the less catastrophic end of the spectrum are variables like flare stars, typically small red dwarf stars that occasionally produce enormous flares, similar to solar flares, but much more powerful relative to the star's total output. These flares can increase the star's brightness by a factor of 2 or more for periods ranging from minutes to hours. Our own Sun is a very mild variable star, with brightness variations of less than 0.1% over its 11-year solar cycle. But some stars similar to the Sun show much larger variations due to star spots, cooler regions on the star's surface similar to sunspots, but covering a much larger fraction of the star. Among the most enigmatic variables are the irregular variables, stars that show brightness changes with no discernible pattern. These include many red giants and supergiants, whose complex atmospheres and strong stellar winds create unpredictable variations in brightness. One particularly interesting example is Betelgeuse, the bright red supergiant marking the shoulder of Orion. Betelgeuse has long been known to be irregularly variable, with brightness changes of up to 1 magnitude over periods of years. But in late 2019 and early 2020, it underwent an unusually deep dimming, fading to about 1/3 of its normal brightness. This great dimming of Betelgeuse sparks speculation that the star might be about to explode as a supernova. However, subsequent observations suggest that the dimming was caused by a combination of the star's normal pulsation cycle and a large dust cloud ejected from its surface, temporarily blocking some of its light from reaching Earth. Betelgeuse has since returned to its normal brightness range, but the event highlighted the unpredictable nature of massive stars and their variability. Betelgeuse is indeed expected to explode as a supernova sometime in the next 100,000 years, a mere blink of an eye in astronomical terms, though the exact timing is impossible to predict. Another class of irregular variables are the luminous blue variables, or LBVs, which we touched on in our discussion of hypergiants. These massive, luminous stars undergo irregular eruptions, sometimes increasing in brightness by several magnitudes. The most famous example is Eta Carinae, which underwent a massive eruption in the 1840s, briefly becoming the second brightest star in the night sky despite its distance of over 7,000 light-years. The underlying mechanism for LBV eruptions isn't fully understood, but it likely involves the star reaching the Eddington limit, where the outward pressure from its intense radiation balances the inward pull of gravity. This creates an unstable situation where small perturbations can trigger massive ejections of material. Turning from intrinsic to extrinsic variables, we encounter the eclipsing binaries, systems where two stars orbit each other in a plane aligned with our line of sight, causing them to eclipse each other periodically. These aren't true variable stars in the sense that the stars themselves aren't changing in brightness, but the system's apparent brightness changes as seen from Earth. Eclipsing binaries provide astronomers with a wealth of information. By carefully analyzing the light curve, a plot of brightness versus time, they can determine the sizes, masses, and orbital characteristics of the stars. For close binary systems, they can even detect distortions in the stars' shapes due to their mutual gravitational pull. A famous example is Algol, also known as Beta Persei, which dims noticeably every 2.9 days when its fainter, larger component partially eclipses its brighter, smaller companion. The brightness change is significant enough that it was noticed by ancient astronomers, who associated the star's winking behavior with evil or misfortune. Algol's name comes from the Arabic phrase Ras al-Ghul, meaning the demon's head. Related to eclipsing binaries are rotating variables. Stars that appear to change in brightness because they're rotating and have non-uniform surface features. These include stars with large star spots, stars with distorted shapes due to rapid rotation, and stars with uneven distributions of elements on their surfaces due to magnetic fields. A particularly interesting subclass of rotating variables are the pulsars, which we discussed in our segment on neutron stars. These rapidly rotating neutron stars emit beams of radiation from their magnetic poles. As they rotate, these beams sweep across Earth like cosmic lighthouses, creating regular pulses of radio waves, X-rays, or other forms of radiation. The pulses are incredibly regular, with periods ranging from milliseconds to seconds, making pulsars some of the most precise natural clocks known. This precision has enabled astronomers to make remarkable discoveries, including the first confirmed exoplanets, planets orbiting a pulsar, and evidence for gravitational waves through the precise timing of pulsar pulses. Variable stars have played a crucial role in the development of astronomy and our understanding of the cosmos. The Cepheid variables, as mentioned earlier, were key to establishing the cosmic distance scale and discovering the expansion of the universe. Studies of RR Lyrae stars have helped map the structure of our galaxy. Observations of eclipsing binaries have provided precise measurements of stellar masses, sizes, and distances. Today, the study of variable stars has been revolutionized by large-scale surveys that monitor millions of stars over long periods, detecting variability that would have been missed by earlier, more targeted observations. Projects like the Optical Gravitational Lensing Experiment, OGIL, the All-Sky Automated Survey for Supernovae, ASAS-SN, and the Zwicky Transient Facility, ZTF, have discovered and classified hundreds of thousands of variable stars. These surveys have revealed that stellar variability is far more common than previously thought. Many stars once considered constant have been found to have small amplitude variations detectable only with precise photometry. The boundaries between different variable types have blurred, with stars showing characteristics of multiple classes or transitioning from one type to another. The future promises even more discoveries. The upcoming Vera C. Rubin Observatory, with its Legacy Survey of Space and Time, LSST, will monitor billions of stars across the southern sky, detecting variability on timescales from minutes to years. This will undoubtedly reveal new classes of variable stars and new physical processes driving stellar variability. Variable stars remind us that the universe is not static, but dynamic, with changes occurring on timescales ranging from seconds to millennia. They challenge us to understand the complex physical processes occurring in and around stars, from nuclear fusion and pulsation to mass transfer and eruptions. And they provide us with valuable tools for measuring cosmic distances, mapping stellar populations, and testing theories of stellar evolution. As we conclude our exploration of variable stars, we're reminded of how much we've learnt from these cosmic flickerers and how much they continue to teach us. From the regular pulsations of Cepheids that helped establish the scale of the universe, to the dramatic eruptions of luminous blue variables that showcase the extremes of stellar behavior, to the precise ticking of pulsars that probe fundamental physics, variable stars enrich our understanding of the cosmos in countless ways. In our next segment, we'll explore another mysterious stellar phenomenon: vanishing stars, objects that appear to disappear from the night sky, challenging our understanding of stellar evolution and raising intriguing questions about what might cause a star to seemingly wink out of existence. So join us as we continue our journey through the strangest stars in the cosmos, venturing ever deeper into the realm of cosmic mysteries and marvels. Before we leave the realm of variable stars, it's worth reflecting on their broader significance. These cosmic flickerers remind us that change is a fundamental aspect of the universe. Stars are not eternal, unchanging beacons, but dynamic entities undergoing complex processes of evolution, interaction, and eventually death. By studying how stars change over time, whether in the regular pulsations of a Cepheid or the catastrophic explosion of a supernova, we gain insights into the life cycles of these cosmic furnaces and their role in the broader cosmic ecosystem. Variable stars also connect us to a long tradition of celestial observation, from ancient astronomers who noticed the winking of Algol to Henrietta Swan Leavitt, who discovered the period luminosity relationship of Cepheids while working as a computer at Harvard College Observatory in the early 20th century, to modern astronomers using automated surveys to monitor millions of stars simultaneously. The study of stellar variability has been a continuous thread in the tapestry of astronomical discovery. As we bid farewell to these flickering cosmic beacons, we carry with us a deeper appreciation for the dynamic nature of stars and the wealth of information their variations provide. In the cosmic ballet of stellar variability, we see the universal principles of physics played out on the grandest of stages, creating patterns of light and dark that have fascinated observers for millennia and continue to yield new discoveries in our modern age. Our journey through the strangest stars in the cosmos has taken us from the ultra-dense neutron stars to the massive hypergiants, from the pulsating Cepheids to the erupting luminous blue variables. Now we venture into perhaps the most mysterious territory yet, the realm of vanishing stars, objects that seem to disappear from the night sky, challenging our understanding of stellar evolution and raising intriguing questions about what might cause a star to seemingly wink out of existence. The concept of a vanishing star might sound like science fiction, but it's a genuine astronomical phenomenon that has puzzled observers for centuries. Historical records contain numerous accounts of stars that were once visible and well documented, only to later become undetectable, even with advanced telescopes. While some of these cases have conventional explanations, others remain enigmatic, pushing the boundaries of our astrophysical understanding. Before diving into specific cases, it's important to understand what we mean by a vanishing star. Stars don't typically disappear suddenly. Their evolutionary timescales are measured in millions or billions of years, far longer than human observational history. When astronomers talk about vanishing stars, they're usually referring to one of several phenomena: a dramatic dimming that renders the star too faint to detect with available instruments, an unusual change in the star's spectral characteristics that makes it unrecognizable, or, in the most extreme cases, an actual end-of-life event that fundamentally transforms the star. One of the earliest documented cases of a vanishing star dates back to the 2nd century BCE, when the Greek astronomer Hipparchus noticed a star that appeared and then disappeared. This observation reportedly motivated him to compile the first comprehensive star catalogue to record what the sky looked like so that future changes could be detected. While the exact nature of what Hipparchus saw remains unknown, it might have been a nova, supernova, or some other transient phenomenon. In more recent times, astronomers have documented numerous cases of stars that appear to have vanished when comparing historical sky surveys with modern observations. One notable project called Where's the Flux, or WTF, specifically looks for stars that were present in earlier surveys but absent in later ones. This project was inspired by the mysterious Tabby's star, officially designated KIC 8462852, which, while not a vanishing star per se, exhibits unusual and dramatic dimming events that have puzzled astronomers. One interesting case of a potentially vanishing star involves an object in the constellation Carina, catalogued as GCVS 1147-619. This star, which was recorded as 11th magnitude in the 1960s, seems to have disappeared by the 1990s. With no detectable source at its recorded position, the star hasn't been detected since, despite searches with increasingly sensitive instruments. Another intriguing case emerged from a study of the Small Magellanic Cloud, a satellite galaxy of our Milky Way. Astronomers comparing observations from the 1950s with more recent data found that a blue supergiant star had apparently disappeared without a trace. This case is particularly interesting because blue supergiants are massive, luminous stars that typically end their lives in spectacular supernova explosions, events that would be hard to miss. Yet no such explosion was observed at the star's location. So what might cause a star to vanish? There are several possibilities, ranging from the mundane to the exotic. One of the most straightforward explanations is simply observational error in the historical record. Early astronomical catalogues were compiled by human observers using relatively primitive instruments, and mistakes were inevitable. A star recorded in an old catalogue might have been a misidentified object, a temporary phenomenon, or even a recording error. When such an object isn't found in later surveys, it's not because it vanished, but because it was never there in the first place. Another conventional explanation is variable brightness. Many stars, as we explored in our previous segment, change in brightness over time. Some, like mirror variables, can dim by factors of hundreds or thousands at regular intervals. Others, like certain types of eruptive variables, might have one-time or very long-period outbursts that temporarily make them much brighter than normal. If a star was catalogued during such an outburst and then returned to its normal, much fainter state, it might appear to have vanished to observers unaware of its variable nature. Proper motion provides another explanation for some apparent disappearances. Stars aren't fixed in the sky but move relative to each other due to their orbits around the galactic center. Over decades or centuries, a star can shift its apparent position by a noticeable amount. If astronomers search for a star at its historically recorded position without accounting for this movement, they might falsely conclude it has vanished when it has simply moved elsewhere. Dust obscuration is yet another possibility. The space between stars is not empty, but filled with gas and dust, the interstellar medium. If a cloud of dust moves between us and a star, it can significantly dim or completely obscure the star's light. This explanation is particularly plausible for stars in or near the galactic plane, where dust is abundant, or for stars known to be surrounded by their own shells of ejected material. But beyond these conventional explanations lie more exotic possibilities that push the boundaries of our understanding of stellar evolution and physics. One such possibility is that some vanishing stars might be failed supernovae. Theoretical models suggest that certain massive stars, under specific conditions, might collapse directly into black holes without the usual supernova explosion. This would cause the star to essentially disappear from view, as its light-emitting surface would be replaced by an event horizon from which no light can escape. While such events would still be expected to produce some transient emission, it might be much fainter than a typical supernova and easily missed, especially for distant stars or those in dusty regions. A related possibility involves a phenomenon called an unnova. This theoretical event occurs when a star collapses to form a black hole, but instead of ejecting its outer layers in a supernova explosion, it quietly accretes them. the star would dim dramatically as its surface is pulled below the event horizon, potentially appearing to vanish from view. Recent theoretical work and simulations suggest that such events might be more common than previously thought, particularly for certain ranges of stellar mass. Another exotic explanation involves something called a merger burst. In a close binary system, two stars might eventually spiral together and merge. Depending on the masses and types of stars involved, this merger could result in various outcomes, including a more massive star, a stellar explosion, or potentially a collapsed object like a black hole. If the merger results in a dramatic change in the system's luminosity or spectral characteristics, it might appear as though the original stars had vanished, replaced by something entirely different or nothing at all. Even more speculative explanations venture into the realm of new physics or extraterrestrial intelligence. Some researchers have suggested that vanishing stars might be evidence of advanced civilizations constructing Dyson spheres or similar megastructures that capture most or all of a star's energy output. While such explanations are highly speculative and should be considered only after exhausting all conventional possibilities, they highlight the potential significance of vanishing star phenomena for multiple fields of study. The search for vanishing stars has been revolutionized by modern astronomical surveys and data analysis techniques. Projects like the Gaia mission, which is creating the most detailed three-dimensional map of our galaxy ever attempted, provide unprecedented data on the positions, movements, and brightness of billions of stars. By comparing this data with historical observations, astronomers can identify candidates for vanishing stars with far greater precision than ever before. Similarly, time domain surveys like the Zwicky Transient Facility and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time will monitor large portions of the sky repeatedly over time, catching transient phenomena and long-term changes that might have been missed in earlier eras. These surveys will likely discover many more candidates for vanishing stars and provide valuable data for understanding their nature. One particularly interesting approach to studying vanishing stars involves examining not just visible light, but multiple wavelengths of the electromagnetic spectrum. A star that has vanished in visible light might still be detectable in infrared, radio, or X-ray wavelengths, providing crucial clues about what happened to it. For example, a star obscured by dust would still emit infrared radiation that could penetrate the dust, while a star that collapsed to form a black hole might be detectable through its accretion disk's X-ray emission. To illustrate the power of multi-wavelength observations, consider the case of N6946, a luminous blue variable star in the Large Magellanic Cloud that was observed to fade dramatically in visible light during the 1990s. Infrared observations revealed that the star wasn't gone, but had ejected a massive shell of dust that was obscuring its visible light. The star itself was heating this dust, which was re-radiating the energy as infrared light. Without these infrared observations, N6946 might have been classified as a vanishing star. Beyond their astrophysical significance, vanishing stars have a certain poetic resonance. They remind us of the impermanence of even the most seemingly eternal cosmic features. Stars that have shone for millions or billions of years can, under the right circumstances, disappear within a human lifetime, or even more rapidly. This impermanence connects to deeper questions about the fate of our sun, our galaxy, and ultimately the universe itself. The fate of our sun, for instance, is to eventually exhaust its nuclear fuel, expand into a red giant, and then shed its outer layers to form a planetary nebula, leaving behind a white dwarf, a dense, Earth-sized remnant that will slowly cool over trillions of years. While this process won't make the sun vanish in the same sense as some of the cases we've discussed, it will fundamentally transform it from the life-giving star we know today into something quite different. On longer timescales, even white dwarfs will eventually cool to become black dwarfs. Cold, dark objects that emit no visible light. None exist yet, as the universe isn't old enough for any white dwarfs to have cooled completely. But in the distant future, many of the stars we see today will effectively vanish in this way. The study of vanishing stars also connects to broader questions about transient phenomena in the universe. From gamma-ray bursts that outshine entire galaxies for a few seconds, to supernovae that briefly rival the brightness of their host galaxies, to gravitational wave events that ripple through space-time itself. The cosmos is filled with fleeting events that come and go on timescales ranging from milliseconds to years. These transient phenomena have become a major focus of modern astronomy, with dedicated observatories and surveys designed to catch and characterize them. Vanishing stars represent one extreme of this spectrum, objects that don't just flare up temporarily, but actually seem to disappear altogether. By studying them, astronomers gain insights not just into unusual stellar evolution pathways, but into the broader question of how things change in our universe. One particularly fascinating aspect of vanishing stars is their potential connection to some of the most exotic objects in the universe, black holes. As we've discussed, one possible fate for a vanishing star is collapse into a black hole without the usual supernova explosion. If confirmed, such events would provide valuable data on black hole formation and evolution, complementing the information gained from observations of black holes in binary systems and the detection of gravitational waves from black hole mergers. The connection to black holes also highlights a profound limitation of astronomy. We can only observe what emits or interacts with electromagnetic radiation or other detectable phenomena like gravitational waves or neutrinos. If a star truly collapses into a black hole and isn't part of a binary system or actively accreting matter, it might become effectively invisible to our instruments. In a very real sense, it would have vanished from the observable universe, even though it still exists as a gravitational singularity. This limitation reminds us that our view of the cosmos is inherently incomplete. Just as vanishing stars might represent objects that have moved beyond our ability to detect them with current methods, there might be entire classes of phenomena that remain invisible to us because they don't interact with our instruments in detectable ways. The discovery and study of vanishing stars thus not only answers specific questions about stellar evolution, but also prompts us to consider what else might be out there, unseen and unknown. As our technological capabilities advance, our ability to detect and characterize vanishing stars will improve. Future space telescopes will provide even more sensitive observations across multiple wavelengths. Gravitational wave observatories will detect more black hole formation events, potentially including some from failed supernovae. And new theoretical models, informed by increasingly sophisticated computer simulations, will help us interpret our observations and predict where and when stars might vanish. In the meantime, the mystery of vanishing stars continues to captivate astronomers and the public alike. Each case represents a cosmic puzzle, a challenge to our understanding, and potentially a window into new physics or astrophysical processes. By studying these stellar disappearing acts, we deepen our comprehension of the life cycles of stars and the dynamic nature of our universe. As we move forward in our exploration of the strangest stars in the cosmos, we'll turn our attention to another class of extreme stellar objects, luminous blue variables, stars that live on the edge of stability, undergoing dramatic eruptions and transformations that showcase the tumultuous nature of massive stars near the end of their lives. These cosmic divas, with their spectacular outbursts and volatile behavior, represent yet another facet of the incredible diversity of stellar phenomena in our universe. Before we leave the realm of vanishing stars, it's worth reflecting on what they teach us about the nature of astronomical knowledge. In earlier centuries, the stars were seen as fixed and eternal, the very embodiment of constancy in a changing world. The discovery that stars are born, evolve, and die, and sometimes seem to vanish before our eyes, transformed our understanding of the cosmos. It reminded us that even the most seemingly permanent features of our universe are subject to change, and that our knowledge is always evolving as we observe more, understand more, and question more. Vanishing stars also highlight the importance of long-term astronomical record-keeping. Without historical star catalogues and photographic plates dating back decades or centuries, many of these disappearances would go unnoticed. In our digital age, preserving astronomical data for future generations becomes even more crucial, ensuring that astronomers centuries from now will be able to compare their observations with ours, just as we compare ours with those of earlier generations. In this way, the study of vanishing stars connects us to both the past and future of astronomical research, a continuing dialogue across time about the nature of our changing cosmos. Among the strangest and most temperamental stars in our universe are the luminous blue variables, or LBVs for short. These cosmic behemoths live their lives on the very edge of stellar stability, like cosmic powder kegs ready to explode at any moment. They are the rock stars of the stellar world, burning bright, living fast, and dying spectacularly. Luminous blue variables are massive stars, typically containing 20 to more than 100 times the mass of our Sun. Their surfaces blaze at temperatures reaching 20,000 to 50,000 degrees Celsius, making them appear brilliantly blue when viewed through telescopes. But what truly sets these stars apart isn't just their size or temperature. It's their unpredictable and often violent behavior. Imagine a star that can suddenly increase its brightness by a factor of 5, 10, or even more within weeks or months. During these outbursts, LBVs can briefly outshine entire galaxies, releasing energy at rates that defy comprehension. Then, just as mysteriously as they flared up, they dim again. This erratic flickering is like nothing else we see in the cosmos. A stellar temper tantrum of the highest order. The cause of this instability lies in the precarious balance between gravity pulling inward and radiation pressure pushing outward. These stars are so massive and burn their nuclear fuel so intensely that they constantly teeter on the edge of self-destruction. The radiation produced in their cores is so powerful that it nearly overcomes the tremendous gravity holding the star together. This creates a situation where even small changes in the star's internal processes can trigger dramatic outbursts visible across vast cosmic distances. What makes luminous blue variables even more fascinating is their short lifespans. While stars like our Sun live for billions of years, LBVs exist for only a few million years at most. They burn through their nuclear fuel with reckless abandon, like cosmic spendthrifts squandering their energy inheritances. This brief existence makes them rare sights in our galaxy, with only a handful identified with certainty. The most famous luminous blue variable, and perhaps the poster child for this stellar class, is Eta Carinae. Located about 7,500 light-years from Earth in the Carina Nebula, this temperamental star has been putting on a cosmic light show for astronomers since the early 19th century. In the 1840s, Eta Carinae underwent what astronomers now call the Great Eruption, briefly becoming the second brightest star in our night sky, despite its enormous distance. During this eruption, Eta Carinae ejected an astonishing amount of material, more than 10 times the mass of our Sun, creating the beautiful bipolar nebula we now see surrounding it, often called the Homunculus Nebula. This expanding cloud of gas and dust continues racing outward at speeds reaching over 2 million kilometers per hour, a lasting reminder of the star's violent outburst. What's even more remarkable is that Eta Carinae isn't just a single star, but a binary system consisting of two massive stars locked in a gravitational embrace. The primary star is a luminous blue variable with about 100 times the mass of our Sun, while its companion, though smaller, is still an impressive 30 times more massive than our star. These twin giants orbit each other every 5.5 years, their gravitational dance adding another layer of complexity to an already extraordinary system. The instability of luminous blue variables makes them prime candidates for spectacular ends. Astronomers believe these stars are likely precursors to some of the most energetic events in the universe, Type Tattoo supernovas. When a luminous blue variable finally exhausts its nuclear fuel, its core collapses under its own gravity, triggering a catastrophic explosion that can outshine entire galaxies for weeks. But some LBVs might meet an even more dramatic fate. The most massive among them are prime candidates to produce hypernovas, supernovas on steroids that are up to 100 times more energetic than regular stellar explosions. These cataclysmic events are so powerful they may be connected to long-duration gamma-ray bursts, the most energetic explosions known in the universe since the Big Bang itself. What makes the study of luminous blue variables crucial to our understanding of the cosmos goes beyond their spectacular light shows. These stars are cosmic forges, creating heavy elements in their cores and then distributing them across space when they explode. The calcium in our bones, the iron in our blood, and the gold in our jewelry were all created in massive stars like these. We are, quite literally, made of star stuff, and LBVs are among the most important contributors to this cosmic recycling program. The material ejected by luminous blue variables also shapes the evolution of their host galaxies. Their powerful stellar winds and eventual explosions create shockwaves that compress surrounding gas clouds, potentially triggering the formation of new stars. This process of stellar feedback is crucial for understanding how galaxies evolve over cosmic time. Observing luminous blue variables presents unique challenges for astronomers. Their rarity means we have limited examples to study, and their unpredictable nature makes it difficult to catch outbursts as they happen. Modern all-sky surveys that continuously monitor large portions of the night sky have improved our chances of spotting these cosmic tantrums. But many questions about LBVs remain unanswered. One of the most intriguing aspects of luminous blue variables is the mechanism that triggers their outbursts. While the general instability between gravity and radiation pressure is understood, the specific processes that push a star over the edge into eruption remain mysterious. Some theories suggest pulsations in the star's outer layers play a role, while others point to interactions with companion stars in binary systems. The study of luminous blue variables has been revolutionized by advances in astronomical instrumentation. Telescopes equipped with spectrographs can analyze the light from these stars, revealing their chemical composition, temperature, and motion through the Doppler effect. Space-based observatories like the Hubble Space Telescope provide sharp images free from atmospheric distortion, showing the complex structures of ejected material around stars like Eta Carinae in stunning detail. Future observatories promise to reveal even more about these cosmic enigmas. The James Webb Space Telescope, with its unprecedented infrared capabilities, allows astronomers to peer through the dust surrounding LBVs to study their behavior in new detail. Ground-based, extremely large telescopes with mirrors spanning 30 meters or more will collect enough light to study luminous blue variables in nearby galaxies, expanding our sample size and helping to answer fundamental questions about these stellar oddballs. As we continue to observe these stars, we're constantly surprised by their behavior. In 2009, astronomers were stunned when a star previously classified as a luminous blue variable in the galaxy NGC 300 million 1 appeared to explode as a supernova, then survived the explosion. This event, designated SN 2009 IP, challenged our understanding of stellar physics and suggested that some LBVs might undergo failed supernovas, where they eject enormous amounts of material without completely destroying themselves. The line between luminous blue variables and other types of massive, unstable stars is sometimes blurry. Wolf-Rayet stars, characterized by their intense stellar winds and high temperatures, may represent a later evolutionary stage of some LBVs. The relationship between these stellar classifications remains an active area of research, with new observations constantly refining our understanding. For the average stargazer, glimpsing a luminous blue variable requires patience and good timing. Even Eta Carinae, the brightest example, is only visible from the southern hemisphere and appears as a modestly bright star to the naked eye during its quiet phases. But with a telescope and good fortune, one might witness one of these stars during an outburst, a rare opportunity to see stellar evolution in action on human timescales, rather than the millions or billions of years such processes usually require. As our journey through the strangest stars in the cosmos continues, These luminous blue variables stand out for their volatility, their brief but spectacular lives, and their crucial role in the chemical enrichment of the universe. They remind us that even stars, which might seem eternal and unchanging to casual observers, can be dynamic, unpredictable, and ultimately transient participants in the great cosmic drama. While vanishing stars puzzle scientists with their mysterious disappearances, stars like Eta Carinae announce their presence with cosmic fireworks displays that demand our attention. As we turn our gaze to other stellar oddities, remember that these unstable giants are among the most influential actors on the cosmic stage, shaping galaxies and seeding space with the elements essential for planets and life itself. When we gaze up at the night sky, each point of light appears to be a solitary star, much like our own sun, shining alone in the vast emptiness of space. But this perception couldn't be further from the truth. In reality, most stars in our galaxy aren't loners at all. They're social creatures, existing in pairs, trios, or even larger groups bound together by gravity's invisible embrace. These stellar partnerships, known as binary and multiple star systems, represent not the exception but the rule in our cosmos, and they create some of the most fascinating and complex stellar arrangements in the universe. Binary star systems, where two stars orbit around their common center of mass, are surprisingly common. Astronomers estimate that more than half of all stars in the Milky Way exist as part of binary pairs or larger groupings. Our solitary sun, it turns out, is somewhat unusual in its single status. This prevalence of stellar partnerships has profound implications for our understanding of how stars form, evolve, and ultimately die. Processes that can be dramatically different when stars don't live in isolation. The dance of binary stars can take many forms, creating a diverse array of stellar partnerships. In some systems, the stars orbit extremely close to each other, completing a revolution in just hours or days. These tight binaries, called contact binaries, can actually touch, with their outer atmospheres merging into a figure-8 shape as they whirl around each other at dizzying speeds. At the other extreme, some binary stars orbit so far apart that they take thousands or even millions of years to complete a single revolution, with distances between them measuring in the trillions of kilometers. This incredible diversity in binary star arrangements creates a classification system based on how we observe them from Earth. Visual binaries are pairs, where both stars can be resolved through telescopes as separate points of light. Spectroscopic binaries reveal themselves not through direct observation, but through the spectral lines in their light, which shift back and forth as the stars move toward and away from us in their orbits. Eclipsing binaries periodically dim as one star passes in front of the other from our perspective, creating mini eclipses that astronomers can measure with extreme precision. Perhaps the most famous binary star system visible to the naked eye is Albireo in the constellation Cygnus. Through even a small telescope, Albireo reveals itself as a stunning pair of contrasting stars, one golden yellow and the other a vibrant blue. This color difference isn't just aesthetically pleasing, it tells us these stars have very different temperatures and ages, with the cooler yellow star being an aging giant and the hotter blue star still in the prime of its life. The visual beauty of Albireo makes it a favorite target for amateur astronomers and a perfect example of how binary stars can reveal stellar diversity in a single glance. Another famous binary is Sirius, the brightest star in our night sky. What appears to the naked eye as a single brilliant point of light is actually a pair consisting of Sirius A, a star twice as massive as our Sun, and Sirius B, a tiny but incredibly dense white dwarf. Sirius B, though only the size of Earth, contains nearly the mass of our Sun compressed into this small volume. The discovery of Sirius B in 1844 helped astronomers understand the end stages of stellar evolution and the existence of compact stellar remnants. Today, we know that many seemingly single stars are actually hiding companion white dwarfs, neutron stars, or even black holes that can only be detected through their gravitational effects or high-energy emissions. The mechanics of binary star systems provide astronomers with one of the few direct methods for measuring stellar masses. By carefully observing the orbital periods and distances between binary stars, scientists can apply Kepler's laws of motion to calculate the masses of each star with remarkable precision. This fundamental data forms the backbone of our understanding of stellar evolution, allowing astronomers to connect a star's mass to its temperature, luminosity, and lifetime. Without binary stars, our knowledge of these basic stellar properties would be far more limited and theoretical. Binary stars also give us a window into stellar evolution that single stars cannot provide. As stars age, they can transfer material to their companions through stellar winds or direct overflow when one star expands into a giant phase. This mass transfer can rejuvenate the receiving star, making it appear younger than it actually is, while drastically altering the evolution of the donor star. These interactions create exotic stellar types that would never form in isolation, such as blue stragglers, which appear to defy the normal aging process of stars in a cluster. One of the most dramatic consequences of binary star evolution occurs when one star ends its life and becomes a compact object, like a white dwarf, neutron star, or black hole. If the companion star later expands and begins transferring material onto this remnant, the stage is set for some of the most energetic phenomena in the universe. Accreting white dwarfs can trigger nova explosions or even catastrophic type Ia supernovae that help astronomers measure cosmic distances. Neutron stars and black holes, pulling material from companion stars, create powerful X-ray sources and relativistic jets that can be detected across vast cosmic distances. Moving beyond simple pairs, trinary star systems, where three stars orbit each other in a gravitational dance, introduce levels of complexity that push the boundaries of our understanding of celestial mechanics. Unlike the relatively stable, predictable orbits of binary stars, three-body systems can exhibit chaotic behavior that defies simple mathematical description. The three-body problem, as it's known in physics, has no general analytical solution, meaning the long-term evolution of triple star systems often requires complex computer simulations to predict. The most famous triple star system visible to the naked eye is Alpha Centauri, our nearest stellar neighbor at just 4.3 light-years away. This system consists of three stars, Alpha Centauri A and B, which are similar to our Sun and orbit each other relatively closely, and Proxima Centauri, a small red dwarf orbiting the pair at a much greater distance. Proxima Centauri, despite being the faintest member of the trio, holds special significance as the closest known star to our solar system, and the host of at least 2 confirmed exoplanets, including one potentially Earth-like world in the habitable zone. The arrangement of stars in triple systems can take several forms. Hierarchical triples, like Alpha Centauri, have 2 stars in a close binary with a third star orbiting the pair at a greater distance. This configuration tends to be more stable over long time periods. In contrast, systems where all 3 stars orbit at comparable distances from each other often become unstable, sometimes ejecting one star entirely or causing stellar collisions. Computer simulations suggest that many triple star systems that formed in the early universe have since been disrupted, with some of the ejected stars becoming high-velocity rogue stars traveling through interstellar space. One of the most intriguing triple star systems discovered in recent years is HR 6819, located about 1,000 light-years from Earth in the constellation Telescopium. Initially thought to contain a black hole visible to the naked eye, more detailed observations revealed a complex system with 3 stars, 2 B-type stars in a close orbit, and a third star circling the pair. The system demonstrates how even expert astronomers can be fooled by the complex interactions in multiple star systems, requiring sophisticated analysis to unravel their true nature. The complexity of multiple star systems extends beyond triples to quadruple, quintuple, and even sextuple star systems. Perhaps the most famous multiple star system is Castor in the constellation Gemini, which appears to the naked eye as a single bright star. but is actually a system of 6 stars, 3 pairs of binaries all gravitationally bound together. Each pair consists of 2 stars orbiting each other closely, while the 3 pairs orbit around their common center of mass in a hierarchical arrangement that has remained stable for billions of years. The prevalence of multiple star systems raises fascinating questions about their formation. How do 2, 3, or more stars form together and establish stable orbits? The leading theory suggests that multiple star systems form when a rotating cloud of gas and dust fragments during its collapse phase, with each fragment eventually becoming a separate star. Another possibility is that stars form individually but become gravitationally bound when they encounter each other within dense stellar nurseries. Computer simulations suggest both processes likely contribute to the diversity of multiple star systems we observe. One of the most intriguing aspects of binary and multiple star systems is their potential for hosting planets. For decades, astronomers questioned whether planets could form and maintain stable orbits around multiple stars, given the complex gravitational fields involved. Science fiction has long imagined worlds with multiple suns, most famously the planet Tatooine from Star Wars with its iconic double sunset. But could such worlds actually exist? The answer, we now know, is a resounding yes. The Kepler Space Telescope revolutionized our understanding of planets in multiple star systems by discovering numerous circumbinary planets, orbiting both stars in a binary system. These planets trace complex paths through space as they orbit the constantly moving center of mass between 2 stars. One of the most famous examples is Kepler 16b, nicknamed Tatooine, after its fictional counterpart. This Saturn-sized planet orbits a pair of stars every 229 days, experiencing dramatic changes in illumination and temperature as it makes its journey around both suns. Even more surprising, astronomers have discovered planets in triple star systems. HD 131399, located about 300 light-years from Earth, hosts at least one gas giant planet orbiting the main star, while 2 companion stars orbit at a greater distance. Computer simulations suggest that planets forming in such complex environments must navigate a gravitational obstacle course, with many potential planetary systems being disrupted before they can fully form. The planets we detect in multiple star systems likely represent the survivors of these challenging formation conditions. The dynamics of multiple star systems also create unique types of variable stars. Algol, also known as the Demon Star, is a famous eclipsing binary where one star periodically passes in front of the other from our perspective, causing the system's overall brightness to dim noticeably. Ancient observers noticed this strange behavior, giving the star its ominous name, but only in the modern era did we understand its true nature. Even more complex are systems like KIC 8462852, discovered by the Kepler mission, where 4 stars create an intricate pattern of mutual eclipses that astronomers playfully nicknamed the 1 in a million eclipsing binary. Computer modeling has revealed that many multiple star systems are metastable rather than permanently stable. Over very long time periods, millions or billions of years, some triple and higher order systems will eventually eject stars or experience radical reconfigurations of their orbits. This dynamic evolution means that the population of multiple star systems we observe today is constantly changing, with new systems forming while others dissolve. Our current snapshot of the galaxy's stellar arrangements represents just one frame in a cosmic film that has been running for billions of years. The interaction between stars in close binary and multiple systems can lead to dramatic stellar metamorphoses. Contact binaries like W Ursae Majoris are so close that their outer atmospheres merge, creating a bridge of stellar material between them. Over time, such systems may completely merge into a single, rapidly rotating star. This process is thought to create rare stellar types like blue stragglers and FK Comets stars, which show properties that cannot be explained by standard single-star evolution. Each of these exotic stellar specimens provides clues about the complex life cycles possible in multiple star environments. One of the most violent events in binary systems occurs when a white dwarf pulls matter from a companion star onto its surface. As hydrogen accumulates on the white dwarf, pressure and temperature build until nuclear fusion ignites explosively across the entire surface in an event called a nova. Unlike supernovae, these thermonuclear explosions don't destroy the white dwarf, allowing the process to repeat when enough new material accumulates. Recurrent novae, like RS Ophiuchi, erupt every few decades, providing astronomers with regular opportunities to study these fascinating stellar explosions. Even more catastrophic are Type Ia supernovae, which occur when a white dwarf in a binary system accumulates enough material to approach the Chandrasekhar limit, about 1.4 times the mass of our Sun. At this point, the white dwarf can no longer support itself against gravity, triggering a runaway fusion reaction that completely destroys the star in a spectacular explosion. Because these events always occur at nearly the same mass threshold, they produce remarkably consistent luminosities, making them valuable standard candles that astronomers use to measure cosmic distances. This application of binary star physics led to the Nobel Prize-winning discovery of the accelerating expansion of the universe. Perhaps the most exotic binary systems contain two compact objects, neutron stars or black holes, orbiting each other. These systems emit gravitational waves, ripples in the fabric of space-time that gradually carry away orbital energy, causing the objects to spiral closer together. The first indirect evidence for gravitational waves came from studying the binary pulsar PSR-B 1913+16, where two neutron stars orbit each other with clockwork precision. The observed decay of their orbit matched Einstein's predictions for gravitational wave emission, earning the 1993 Nobel Prize in Physics. In 2015, the LIGO and Virgo collaborations made history by directly detecting gravitational waves from two black holes merging 1.3 billion light-years away. This groundbreaking discovery opened a new window on the universe, allowing astronomers to hear the cosmic collisions of compact objects formed in the death throes of massive binary stars. Each gravitational wave detection tells the story of a binary system's dramatic end, providing unprecedented insights into black hole and neutron star properties that would be impossible to obtain through conventional astronomy. The study of binary and multiple star systems exemplifies how astronomical observations can drive advances in theoretical physics. The three-body problem, first formulated by Isaac Newton in the 17th century, remains one of the most famous unsolved problems in classical mechanics. While no general analytical solution exists, astronomers and mathematicians have developed sophisticated numerical methods to predict the behavior of multiple star systems over long time periods. These computational advances have applications far beyond astronomy, influencing fields from weather prediction to quantum mechanics. For observers equipped with small telescopes, binary stars offer some of the most visually appealing targets in the night sky. Beyond the famous examples of Albireo and Alpha Centauri, hundreds of visual binaries are within reach of amateur equipment. Many display striking color contrasts between their component stars, reds paired with blues, yellows with whites, creating celestial jewels scattered across the firmament. These color differences reflect the different temperatures, masses, and evolutionary stages of the component stars, turning aesthetic appreciation into a pathway for understanding stellar physics. The future of multiple star research looks especially promising with the advent of new observational technologies. The European Space Agency's Gaia mission is mapping the precise positions and motions of over 1 billion stars, revealing previously unknown binary and multiple systems through subtle gravitational perturbations in stellar movements. Meanwhile, the James Webb Space Telescope's unprecedented infrared sensitivity allows astronomers to peer through dust clouds that often obscure young multiple star systems, providing new insights into how these complex arrangements form and evolve in their earliest stages. As our journey through the strangest stars in the cosmos continues, Binary and multiple star systems remind us that the universe rarely favors simplicity. The complex gravitational dances of 2, 3, or more stars challenge our mathematical models while creating conditions for some of the most exotic and energetic phenomena in astronomy. From the gentle eclipses of Algol to the cataclysmic mergers of binary black holes, these stellar partnerships write cosmic stories far more intricate than any single star could tell alone. While some stars shine in eerie isolation, the vast majority prefer company, forming the social fabric of our galaxy through their gravitational connections. Next, we turn our attention to perhaps the most extreme stellar partnerships of all, stars that orbit in the gravitational grip of black holes, where the dance of life and death plays out against the backdrop of the most mysterious objects in the universe. In the vast theatre of cosmic wonders, few partnerships are as dramatic or consequential as those between ordinary stars and black holes. These unlikely couples engage in a deadly dance of gravity and matter, creating some of the most energetic and violent phenomena in the universe. Black hole star systems represent the ultimate asymmetric relationship. One partner, a giver of light, heat, and matter. The other, an insatiable gravitational abyss from which nothing, not even light itself, can escape. As we delve into these extraordinary stellar arrangements, we'll witness the universe at its most extreme, where the laws of physics are pushed to their absolute limits. Black holes themselves remain among the most enigmatic objects in astronomy. Born from the catastrophic collapse of massive stars, stellar mass black holes typically contain between 5 and several dozen times the mass of our Sun, all compressed into a region smaller than a city. At the center lies the singularity, a point of infinite density where our current understanding of physics breaks down completely. Surrounding this is the event horizon, the infamous point of no return beyond which escape becomes impossible. Yet despite their fearsome reputation, disk, and the jets it launches, to wobble over time, the result is one of the most beautiful and dynamic structures in our galaxy. A cosmic corkscrew, writing the story of this deadly dance in trails of superheated plasma stretching across light years of space. The transfer of material in black hole binaries doesn't occur steadily, but often happens in dramatic outbursts. Many systems exist in a mostly quiescent state for years or decades, with only a trickle of material flowing from the companion star to the black hole. Then, triggered by instabilities in either the star or the accretion disk, a sudden flood of material creates a dramatic brightening event called an X-ray nova. During these episodes, which typically last weeks to months, a previously invisible system can become one of the brightest X-ray sources in the sky, increasing in brightness by factors of thousands or even millions before gradually fading back to quiescence. One of the most famous recurring X-ray novae is GRS 1915 plus 105, which erupts approximately every 30 to 40 years. During its 1992 outburst, this system briefly became the brightest X-ray source in the sky, emitting more high-energy radiation than any object except the Sun. Detailed observations revealed a black hole about 12 times the mass of our Sun orbited by a normal star in a period of just 33 days. The system's recurring outbursts may be triggered by instabilities in the companion star's atmosphere, causing periodic dumps of material onto the hungry black hole. The properties of the companion star in a black hole binary largely determine the system's behavior and appearance. High-mass X-ray binaries pair black holes with massive, hot stars like blue supergiants or Wolf-Rayet stars. These massive companions lose material through powerful stellar winds, which the black hole intercepts and accretes. In contrast, low-mass X-ray binaries contain smaller companion stars, similar to or less massive than our Sun. These stars don't have strong stellar winds, so material transfer occurs primarily when the star overflows its Roche lobe, the region within which material remains gravitationally bound to the star rather than the black hole. The most extreme form of matter transfer occurs when the companion star fills and exceeds its Roche lobe. creating a flood of material onto the black hole. This process, called Roche lobe overflow, happens when the companion star expands during its evolution or when the orbital separation shrinks due to gravitational influences. The result is a direct stream of stellar material flowing from the star to the black hole through what's called the L1 Lagrangian point, the gravitational balance point between the two objects. This stream doesn't fall directly into the black hole, but forms the accretion disk due to the conservation of angular momentum, much like water spiraling down a drain rather than falling straight in. Black hole binaries aren't permanent arrangements. Over time, the companion star loses mass to the black hole, altering the orbital dynamics of the system. In some cases, especially with massive companion stars, this mass transfer happens so rapidly that the black hole can't efficiently accrete all the incoming material, creating an unstable situation that may eventually engulf both objects in a common envelope of stellar material. The ultimate fate of such systems depends on many factors, including the masses of both objects, their evolutionary states, and their orbital characteristics. For systems with lower mass companion stars, the mass transfer can continue for billions of years, gradually whittling away the star until only its dense core remains. This process may eventually transform a normal star into a white dwarf, creating a black hole white dwarf binary. These systems are expected to be common but difficult to detect due to their relatively low energy output compared to systems with normal stellar companions. Future gravitational wave observatories may be our best hope for identifying these quiet but numerous binaries. The study of black hole binaries took a revolutionary leap forward with the detection of gravitational waves from merging black holes. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in spacetime from two black holes, each roughly 30 times the mass of our Sun, spiraling together and merging into a single larger black hole 1.3 billion light-years away. This historic detection not only confirmed a major prediction of Einstein's general relativity, but opened an entirely new window on black hole binary systems at the moment of their most dramatic interaction, their final merger. Since that first detection, dozens more black hole mergers have been observed through gravitational waves, revealing a population of black hole binaries that was previously invisible to traditional astronomy. These observations prove that black holes can form paired systems with other black holes, not just with normal stars. The most likely origin for these black hole pairs is from binary star systems, where both stars were massive enough to end their lives as black holes, though other formation pathways involving dense stellar clusters or primordial black holes from the early universe remain possibilities. One of the most extraordinary discoveries about black hole binaries comes from studying how they affect space-time itself. The intense gravity of a rapidly spinning black hole literally drags the fabric of space-time around it in a process called frame dragging or the lens-thurring effect. In binary systems, this dragging can influence the orbit of the companion star and the behavior of the accretion disk. For black holes spinning at nearly the maximum possible rate, this effect creates a region called the ergosphere, outside the event horizon, where space itself is forced to rotate in the same direction as the black hole, with profound implications for the energetics of the system. The extreme physics of black hole binaries makes them natural laboratories for testing general relativity and other theories of gravity. By carefully measuring the orbital motions of stars around black holes, astronomers can check whether gravity behaves exactly as Einstein predicted under the most extreme conditions nature provides. So far, general relativity has passed every test with flying colors, but future observations with even greater precision might reveal subtle deviations that could point toward new physics beyond Einstein's century-old theory. One of the most challenging aspects of studying black hole binaries is simply finding them. Despite their energetic emissions, these systems can be difficult to identify conclusively. Astronomers typically look for a combination of signatures, periodic X-ray emissions, evidence of an accretion disk in the spectrum, and most importantly, measurements of the invisible companion's mass through its gravitational influence on the visible star. If this invisible companion exceeds about 3 solar masses, the theoretical maximum mass for a neutron star, it's likely a black hole. Using these methods, astronomers have confirmed several dozen black hole binaries in our galaxy, though theoretical models suggest thousands more remain undiscovered. Recent advances in observational techniques have led to the discovery of a new class of black hole binaries that don't fit neatly into the traditional categories. In 2019, astronomers announced the discovery of a system designated HR 6819b, which appeared to contain a black hole about 4 times the mass of our Sun, smaller than any previously confirmed black hole. This finding challenged theories about the minimum possible mass for a black hole formed through stellar collapse. However, subsequent analysis suggested the system might actually contain a close pair of stars, rather than a black hole, highlighting the ongoing challenges in definitively identifying these elusive objects. The quest to find dormant black hole binaries, systems where little or no material is actively falling onto the black hole, received a major boost from the European Space Agency's Gaia mission. By measuring the positions and motions of over 1 billion stars with unprecedented precision, Gaia can detect the subtle wobbles in a star's movement caused by an invisible companion's gravitational pull. In 2022, astronomers using Gaia data identified Gaia BH1, a system containing a roughly 10 solar mass black hole orbited by a Sun-like star. Unlike most known black hole binaries, this system shows almost no accretion activity, making it a representative of the large population of silent black holes predicted to exist throughout our galaxy. Black hole binaries also play crucial roles in the evolution of galaxies. When galaxies merge, their central supermassive black holes, millions or billions of times more massive than stellar black holes, can form binary systems that eventually coalesce. These supermassive black hole binaries generate gravitational waves of much lower frequency than those from stellar mass systems, potentially detectable by future space-based gravitational wave observatories like LISA, Laser Interferometer Space Antenna. By studying how black holes pair up and merge across all mass scales, from stellar to supermassive, astronomers hope to build a complete picture of how these objects influence cosmic evolution. The material stolen from companion stars doesn't just disappear forever when it crosses a black hole's event horizon. According to Stephen Hawking's groundbreaking theoretical work, black holes should slowly evaporate over time through a quantum process called Hawking radiation. However, for stellar mass black holes, this evaporation is incredibly slow, taking many times the current age of the universe to complete. In practical terms, the material consumed from companion stars becomes effectively permanent additions to the black hole's mass, gradually increasing its size and strengthening its gravitational influence over cosmic timescales. One of the most intriguing possibilities for black hole binaries involves planets. Could planets exist in these extreme systems, either orbiting the companion star, the black hole itself, or both objects? Computer simulations suggest that planets could indeed maintain stable orbits in some black hole binary configurations, though they would experience wildly varying conditions as they move through the complex gravitational landscape. Any planets that formed before the black hole's creation might survive if their orbits were wide enough to avoid disruption during the supernova that created the black hole. The discovery of such planets would represent an extraordinary addition to the already diverse exoplanet catalogue. For science fiction writers and imaginative astronomers alike, the environment near a black hole binary presents one of the most extreme and visually striking settings in the universe. Imagine standing on a hypothetical planet orbiting the companion star in such a system. The sky would be dominated by the black hole's accretion disk, a brilliant multicolored ring of superheated gas surrounding an absolutely black circle where no light escapes. Powerful jets might extend from the central darkness like cosmic searchlights, while the disk itself would likely flicker and pulse as clumps of material spiral inward. The relativistic effects near the black hole would create optical illusions where the far side of the accretion disk appears to bend over the top of the black hole due to the extreme curvature of space-time. The study of black hole binaries intersects with one of the most profound questions in modern physics, the information paradox. When matter falls into a black hole, what happens to the quantum information it contained? According to quantum mechanics, information cannot be destroyed, yet material crossing the event horizon seems lost forever. Recent theoretical work suggests that this information might be encoded in subtle quantum correlations in the Hawking radiation or in quantum structures at the event horizon itself. Black hole binaries, with their steady supply of infalling material, represent natural experiments in this cutting-edge area where general relativity meets quantum mechanics. As our observational capabilities advance, black hole binaries continue to surprise us with their diversity and complexity. In 2020, astronomers reported a black hole binary system called MAXI J1820+070 with an orbital period of just 28 minutes, the shortest ever detected. In this remarkably compact system, a white dwarf star orbits a black hole at a distance smaller than the radius of our Sun, completing more than 50 orbits every day. The extreme proximity creates intense gravitational stresses that cause the white dwarf to slowly disintegrate, feeding a steady stream of material to the black hole. Another extraordinary discovery came in 2019 with the detection of a triple system containing a black hole and two stars all orbiting each other. Designated HR 6819, this system, about 1,000 light-years from Earth, contains an inner binary of two stars orbiting each other every 40 days, with a black hole about 4 times the mass of our Sun in a much wider orbit around the pair. Such hierarchical arrangements provide valuable insights into how black holes interact with multiple stars and the complex evolutionary pathways that can lead to these exotic stellar configurations. The future of black hole binary research looks exceptionally promising, with new observatories coming online in the next decade. The Vera C. Rubin Observatory will conduct a 10-year survey of the southern sky, potentially discovering thousands of new black hole binary systems through their optical variability. Meanwhile, the next generation of X-ray telescopes like ESA's Athena will provide unprecedented views of the hot accretion disks surrounding black holes. Combined with improved gravitational wave detectors capable of seeing more distant and diverse mergers, these observatories will revolutionize our understanding of black hole binaries across all stages of their evolution. Perhaps the most profound aspect of black hole binaries is what they teach us about cosmic cycles. The material stripped from companion stars and consumed by black holes isn't truly lost to the universe. When black holes merge, they release enormous energy in gravitational waves. And in the extremely distant future, as black holes complete their evaporation through Hawking radiation, they return all their accumulated mass energy to the universe in the form of particles and radiation. In this way, black hole binaries participate in the grand cosmic recycling program, transforming stars into black holes into radiation, and potentially that radiation into new stars and planets in a cycle that could continue for trillions upon trillions of years. As our journey through the strangest stars in the cosmos continues, black hole binaries represent perhaps the most extreme stellar partnerships we've encountered, where one partner has undergone the ultimate stellar transformation into an object so dense that it tears at the fabric of space-time itself. These systems push our understanding of physics to its limits while providing some of the most energetic and dynamic phenomena in astronomy, from the brilliant accretion disks to the relativistic jets and the gravitational waves from their final mergers. Black hole binaries offer windows into the most extreme physics our universe has to offer. Having explored these deadly dances between stars and the darkest objects in the cosmos, we now turn to our final frontier. Stars that challenge not just our understanding of astrophysics, but possibly our place in the universe. Could some stars behave in ways that suggest more than natural processes at work? Let's explore the controversial and fascinating realm of stars that might not be entirely what they seem. As we reach the final chapter in our exploration of the strangest stars in the cosmos, we venture into perhaps the most speculative territory of all, the possibility that some unusual stellar phenomena might, just might, have explanations beyond conventional astrophysics. Throughout human history, we've explained the inexplicable by invoking intelligence or intent, only to later discover natural processes at work. Yet, as our understanding of the universe deepens, so too does our appreciation for how advanced technological civilizations might interact with their stellar environments. The question emerges, could some bizarre stellar behavior represent the handiwork of advanced alien civilizations? Let's examine this fascinating intersection of astronomy, physics, and the search for extraterrestrial intelligence. The concept of artificially modified stars isn't just science fiction. It has a serious scientific pedigree dating back decades. In 1960, physicist Freeman Dyson published a paper in the journal Science, suggesting that advanced civilizations would inevitably seek to capture more and more of their parent star's energy. The most efficient way to do this, he reasoned, would be to construct a vast swarm of solar collectors completely surrounding their star, a structure later dubbed a Dyson sphere. Such a megastructure wouldn't be a solid shell, but rather a vast collection of orbiting platforms, satellites, and habitats that collectively intercept most of the star's radiant energy for technological use. From an astronomical perspective, a star surrounded by a Dyson sphere would appear highly unusual, since most of the visible light would be captured and utilized by the alien civilization. The star would seem abnormally dim in optical wavelengths. However, all that captured energy would eventually be re-radiated as waste heat, making the system unusually bright in infrared wavelengths. This distinctive infrared excess would create a spectral signature unlike natural stars, one that might be detectable across interstellar distances. The search for Dyson spheres represents one of the more serious scientific approaches to finding advanced extraterrestrial civilizations. Several astronomical surveys have specifically looked for stars with infrared signatures consistent with partial Dyson spheres, though no conclusive candidates have been identified. The most comprehensive search was conducted using data from the WISE, Wide Field Infrared Survey Explorer Space Telescope, which mapped the entire sky in infrared wavelengths. While researchers found numerous stars with unusual infrared properties, all had potential natural explanations, such as surrounding dust clouds or normal stellar aging processes. Beyond complete Dyson spheres, advanced civilizations might construct other stellar megastructures with distinctive observational signatures. Dyson rings or swarms might only partially encompass a star, capturing a fraction of its energy while creating unusual transit signatures as the structures pass between the star and our line of sight. Such partial obstruction could cause irregular dimming patterns, unlike those produced by natural phenomena like planets or dust clouds. The star might appear to flicker or dim in ways that defy conventional astrophysical explanations. In 2015, astronomers observed precisely this kind of unusual dimming behavior in a star designated KESE 8462852, more popularly known as Tabby's star, after lead researcher Tabitha Boyajian. This otherwise ordinary F-type star exhibited strange, irregular dimming events, where its brightness decreased by up to 22%, far more than could be explained by even a Jupiter-sized planet. Moreover, the dimming patterns were asymmetric and irregular, without the predictable periodicity expected from orbiting planets. The bizarre behavior of Tabby's star sparked widespread speculation, including the possibility that astronomers were seeing the transit of artificial structures, perhaps even a partially constructed Dyson sphere. This explanation was considered seriously enough that the SETI, Search for Extraterrestrial Intelligence, Institute aimed radio telescopes at the star, searching for artificial signals that might indicate technological activity. None were found, and subsequent observations have favored natural explanations involving irregular dust clouds, possibly from disintegrating comets or planetary collisions. Nevertheless, Tabby's star demonstrated how unusual stellar behavior can briefly make even mainstream astronomers consider artificial causes. Another star that generated excitement in the SETI community is EPIC 204278916, better known as Boyajian's star. Like Tabby's star, it exhibits irregular dimming events, but with the added mystery of long-term dimming over decades. Since its discovery, astronomers have proposed various natural explanations, from circumstellar dust to internal changes in the star itself. While the alien megastructure hypothesis has faded as more data accumulates, the star continues to defy simple explanation, illustrating the challenge of distinguishing truly artificial phenomena from unusual natural processes we don't yet fully understand. Beyond passive energy harvesting structures like Dyson spheres, truly advanced civilizations might actively modify or engineer stars to suit their needs. Theoretical physicist Clement Vidal has explored the concept of stellification, the hypothetical process of creating artificial stars or modifying existing ones. Such stellar engineering could involve adjusting a star's fusion processes, perhaps to extend its lifetime, alter its luminosity, or even change its chemical composition to produce specific elements needed by an advanced civilization. One method of stellar engineering might involve injecting elements into a star's core to catalyze different fusion reactions. For instance, adding carbon to a hydrogen-burning star creates a CNO, carbon-nitrogen-oxygen, fusion cycle that produces energy more efficiently at certain temperatures than the proton-proton chain reaction that powers our Sun. An advanced civilization might perform such catalytic stellar engineering to increase a star's energy output without significantly shortening its lifespan. More extreme stellar engineering could involve creating entirely artificial stars through controlled fusion. Rather than relying on natural stars with their inevitable aging and death, an advanced civilization might construct self-sustaining fusion reactors on a stellar scale. These artificial stars could be optimized for stability, longevity, and specific energy outputs tailored to the civilization's needs. From our perspective, such engineered stars might exhibit unusual spectral signatures, unexpected stability, or other anomalous properties that differentiate them from natural stars following standard evolutionary paths. Some astronomers have even suggested that white dwarfs, the dense, cooling remnants of stars like our Sun, might be attractive targets for advanced engineering. A civilization could potentially mine these stellar corpses for heavy elements created during the star's lifetime, or even reignite fusion through careful manipulation. White dwarfs with unexpected properties or behaviors might warrant closer examination through this speculative lens, though again, natural explanations should always be prioritized. The concept of stellar lifting represents another form of potential stellar engineering within the theoretical capabilities of highly advanced civilizations. This process would involve removing material from a star's outer layers, perhaps using powerful magnetic fields to extract plasma along the star's magnetic field lines. A civilization might pursue stellar lifting to harvest valuable elements, reduce a star's mass to extend its lifespan, or adjust its luminosity to better suit inhabited worlds. A star undergoing artificial stellar lifting might exhibit unusual mass loss rates or distinctive pectoral features inconsistent with natural stellar wind processes. One of the more exotic proposals for artificial stellar modification comes from theoretical physicist Clement Vidal, who suggests advanced civilizations might create or maintain quasars as power sources. Quasars are among the most energetic objects in the universe, powered by supermassive black holes accreting matter at prodigious rates. While natural quasars are typically found in the distant early universe, the discovery of a quasar-like object in our cosmic neighborhood with unexplainable properties might, in this highly speculative scenario, warrant consideration as an artificial power source. Beyond energy production, advanced civilizations might modify stars for computational purposes. In 2012, theoretical physicist Gregory Laughlin and colleagues proposed the concept of stellar engines. megastructures that would use a star's energy to power vast computational systems. A star surrounded by such computational architecture might exhibit unusual pulsation patterns or energy distributions as the civilization harvests and utilizes the star's output in complex, highly engineered ways. The energy consumption patterns of such a system could potentially create observable signatures distinct from natural stellar phenomena. Some SETI researchers have suggested focusing on unusual stellar pulsations or variability as potential technosignatures. While many stars pulsate due to natural internal processes, artificial manipulation of a star's outer layers could theoretically produce precisely controlled pulsations, perhaps even encoding information. Astronomers Ross Church and Nick Rea have proposed that civilizations might use stellar pulsations as beacons, creating distinctive patterns easily distinguishable from natural variability. Such stellar SETI remains highly speculative, but represents a creative approach to searching for evidence of advanced engineering. The boundaries between theoretical stellar engineering and speculative science fiction becomes increasingly blurred when considering truly advanced civilizations, those that might exist millions or billions of years beyond our current technological level. Physicist Nikolai Kardashev proposed a classification system for such civilizations based on their energy utilization. Type 1 civilizations harness all the energy available on their planet. Type 2 civilizations utilize the entire energy output of their star, and Type 3 civilizations control the energy of their entire galaxy. The stellar modifications we've discussed would generally fall within the capabilities of Type 2 civilizations, while more exotic possibilities might emerge for Type 3 entities. A Type 3 civilization might not just modify individual stars, but engineer entire stellar populations. They might ignite star formation in otherwise dormant regions, extend the lifespans of valuable stars, or even move stars to create more favorable configurations. Astronomers have occasionally observed stars with velocities or positions that defy easy explanation, so-called hypervelocity stars moving fast enough to escape our galaxy, or stars in unusual arrangements. While natural explanations involving gravitational interactions almost certainly account for these observations, they illustrate the kind of anomalies that might, in principle, result from large-scale stellar engineering by a sufficiently advanced civilization. If advanced civilizations do modify stars for technological purposes, how might we distinguish their handiwork from natural phenomena? Astronomer Jason Wright suggests looking for objects that appear to violate the second law of thermodynamics, the principle that entropy or disorder in a closed system always increases over time. Natural processes tend toward greater entropy, while technological interventions often create localized decreases in entropy through the application of energy and information. Stars exhibiting entropy-defying characteristics might warrant closer examination, though identifying such characteristics requires careful analysis and a thorough understanding of natural stellar processes. Perhaps the most important point to emphasize is that extraordinary claims require extraordinary evidence. Throughout the history of astronomy, apparently inexplicable phenomena have eventually yielded to natural explanations. When pulsars were first discovered in 1967, their precisely timed radio pulses were so regular that they were briefly labeled LGM for little green men, before their true nature as rapidly rotating neutron stars was understood. This history counsels caution when interpreting unusual stellar behaviors. While we should remain open to the possibility of artificial structures or engineering, natural explanations should always be our first consideration. The field of astrobiology and SETI research encounters an inherent challenge when considering potential alien megastructures, the anthropic principle. We can only imagine technologies based on our understanding of physics and our own developmental trajectory. Advanced civilizations might utilize physical principles or technologies completely beyond our current comprehension, creating signatures we wouldn't even recognize as artificial. As Arthur C. Clarke famously observed, any sufficiently advanced technology is indistinguishable from magic, or in this context, perhaps indistinguishable from an unusual natural phenomenon. If advanced civilizations do modify stars, the The most detectable examples might be those still in progress, stars undergoing active engineering, rather than those where the modification is complete and stable. Such transitional states might exhibit more obvious anomalies as the star moves from its natural state to an engineered one. Monitoring large populations of stars for unexpected transitions or evolutionary behaviors could potentially identify candidates for closer examination. The challenge lies in distinguishing genuinely anomalous behavior from the already diverse range of natural stellar phenomena. Recent advances in astronomical observation have dramatically increased our ability to detect subtle stellar anomalies. The Gaia Space Observatory has mapped the positions, motions, and physical properties of over 1 billion stars with unprecedented precision. The Transiting Exoplanet Survey Satellite, TESS, monitors thousands of nearby stars for minute changes in brightness. Future observatories like the James Webb Space Telescope and the Vera C. Rubin Observatory will further enhance our ability to characterize unusual stars. These technological advances ensure that any stellar anomalies significant enough to suggest artificial modification will increasingly fall within our detection capabilities. The search for artificial structures around stars represents a fascinating intersection of astronomy and SETI research, one that allows for the possibility of detecting advanced civilizations through their large-scale engineering projects rather than intentional communications. The field remains highly speculative, but grounded in sound physical principles and observational strategies. As our understanding of stellar physics deepens and our observational capabilities improve, we can more confidently distinguish truly anomalous stellar behavior from the already rich tapestry of natural stellar phenomena. As we search for potential technosignatures around distant stars, we should also consider how our own star might appear to distant observers. Our civilization has already begun modest forms of stellar engineering, launching solar observatories and developing technologies to harness solar energy. While these efforts are far too small to be detectable across interstellar distances, they represent the beginning of our own interaction with our parent star. Future generations might deploy more substantial solar energy collectors or even implement climate engineering projects that would alter Earth's reflectivity or atmospheric properties in ways potentially detectable by distant astronomers. The concept of stellar engineering also raises profound philosophical questions about the relationship between intelligence and the cosmos. If consciousness and technology are natural outgrowths of cosmic evolution, then artificially modified stars would represent not an interruption of natural processes, but their continuation through new means. The boundary between the natural and the artificial blurs when we consider that intelligence itself emerges from and remains part of nature. Perhaps the capacity for stars to be modified by the intelligent life they help create represents another aspect of stellar evolution, one that becomes possible only after billions of years of cosmic development. For now, the evidence for artificially modified stars remains entirely theoretical. Every unusual stellar phenomenon observed to date has either been explained through natural processes or remains under investigation, with natural hypotheses as the leading contenders. The vast energy requirements, engineering challenges, and timescales involved in stellar modification place such projects well beyond our current technological capabilities, making it difficult to assess their feasibility, even in principle. Yet the search continues, driven by humanity's enduring curiosity about whether we share our universe with other technological civilizations. If we ever do confirm the existence of artificial stellar engineering, the implications would be profound. Such a discovery would not only answer the ancient question of whether we are alone in the universe, but would also suggest that technological civilizations can achieve longevity and capabilities far beyond our current level. It would provide evidence that the challenges facing our own civilization, resource limitations, energy needs, climate stability, can be overcome through sufficiently advanced technology and social organization. The discovery of even one artificially modified star would transform our understanding of our place in the cosmos and the potential future of our own species. As our journey through the strangest stars in the cosmos concludes, we find ourselves at the frontier where established science meets speculation, where the known universe opens to possibilities we can barely imagine. From neutron stars with their extreme densities to hypothetical quark stars, from the unstable luminous blue variables to the mysterious vanishing stars, and finally to the speculative realm of artificial stellar engineering, we've explored the full spectrum of stellar strangeness. These cosmic oddities challenge our understanding, expand our horizons, and remind us that the universe remains full of wonders waiting to be discovered. Whether the unusual stars we observe represent natural phenomena we don't yet fully understand, or the remote possibility of artificial intervention, they continue to drive the advancement of astronomy and human knowledge. Each strange stellar object raises new questions, inspires new observations, and pushes the boundaries of our theories. In this ongoing dialogue between observation and explanation, between mystery and understanding, we find the essence of scientific progress and the enduring human quest to comprehend our place among the stars. As we now turn to our final thoughts on these cosmic wonders, we carry forward this spirit of curiosity and discovery that has guided our exploration of the strangest stars in the cosmos. As our cosmic journey through the strangest stars in the universe comes to a close, we find ourselves with more questions than answers, exactly as it should be in the grand adventure of scientific exploration. We've traveled across light years and peered into some of the most extreme environments the cosmos has to offer. From the crushing densities of neutron stars to the unstable brilliance of luminous blue variables, from the quantum weirdness of hypothetical quark stars to the deadly dance of black hole binaries, each strange stellar specimen has offered us a unique window into the fundamental forces that shape our universe and push the boundaries of our understanding. Now, as we reflect on this voyage, let's consider what these cosmic oddballs collectively tell us about the universe and our place within it. Strange stars remind us, first and foremost, of the astonishing diversity of the cosmic landscape. Our Sun, the star we know best and the one that makes life on Earth possible, represents just one point in an incredibly vast parameter space of stellar possibilities. The universe has spent nearly 14 billion years experimenting with different combinations of mass, composition, rotation, magnetic fields, and environmental conditions to produce the rich tapestry of stellar phenomena we observe today. From tiny red dwarfs, barely massive enough to sustain fusion, to hypergiant stars that would engulf Jupiter's orbit if placed in our solar system. From solitary wanderers drifting through intergalactic space to complex hierarchical systems with half a dozen stellar members, the variety seems endless. This diversity itself contains a profound message. The universe explores all possibilities permitted by the laws of physics. Given enough time and space, matter arranges itself into all viable configurations, pushing against the boundaries of what's physically possible. The strangest stars often exist precisely at these boundaries. Neutron stars at the edge of gravitational collapse, quark stars at the transition between forms of matter, luminous blue variables at the limit of stellar stability. By studying these extreme cases, we gain invaluable insights into the fundamental physical laws that govern everything from the smallest subatomic particles to the largest cosmic structures. The strange stars we've explored also highlight the dynamic, ever-changing nature of the cosmos. Stars are not eternal, unchanging beacons as they might appear to casual observation. They are born, evolve, and die, often dramatically. Many undergo radical transformations throughout their lifespans. Peaceful hydrogen-burning stars can become bloated red giants, explosive supernovae, exotic neutron stars, or light-trapping black holes. Some engage in complex interactions with companion stars, exchanging material and altering each other's evolutionary paths. Others influence their surroundings through powerful stellar winds, radiation, and element formation, shaping the next generation of stars and planetary systems. This constant change and evolution extends beyond individual stars to the universe as a whole. The very first stars formed from pristine hydrogen and helium created after the Big Bang had compositions and behaviors quite different from stars born in the present era. The strangest stars we've discussed are themselves waypoints in cosmic evolution. Each generation of stars produces heavier elements that make new types of stars and stellar phenomena possible. Even the life cycle of a single strange star can transform the surrounding interstellar medium, seeding it with heavy elements and energy that will influence star formation for billions of years to come. One of the most remarkable revelations from our survey of strange stars is the deep interconnection between the microscopic and the macroscopic, between particle physics and astrophysics. Neutron stars and hypothetical quark stars represent states of matter that cannot be created in terrestrial laboratories, where atomic nuclei break down into their constituent particles under unimaginable pressures. The interiors of massive stars function as cosmic nuclear fusion reactors, building complex elements from simpler ones through processes that researchers struggle to replicate even momentarily on Earth. Black holes create conditions where general relativity and quantum mechanics, our two most successful but incompatible theories of physics, must somehow reconcile, offering potential glimpses into a more complete understanding of fundamental reality. This connection between stars and subatomic particles reminds us of our own intimate relationship with the cosmos. The elements that form our bodies, the carbon in our cells, the oxygen we breathe, the calcium in our bones, the iron in our blood, were all forged in the nuclear furnaces of stars that lived and died before our sun was born. The most exotic and violent stars play particularly important roles in this cosmic recycling program. Luminous blue variables eject massive amounts of processed elements into space during their periodic outbursts. Colliding neutron stars create the conditions necessary to form the heaviest elements like gold and platinum. Even the radio waves from pulsars and the X-rays from black hole binaries provide unique tools for probing the composition and structure of interstellar space. The study of strange stars has also driven remarkable technological innovation. To observe neutron stars pulsing in radio waves, X-rays, and gamma rays, astronomers have developed increasingly sensitive detectors and sophisticated data analysis techniques. To detect the gravitational waves from merging black holes and neutron stars, physicists built the most sensitive measuring devices ever created, capable of detecting distortions in spacetime smaller than the width of a proton. To understand the extreme physics of these objects, theorists have pushed mathematical models and computer simulations to their limits, developing new computational tools with applications far beyond astrophysics. The quest to understand cosmic mysteries consistently drives human ingenuity forward. Our exploration of strange stars also highlights the evolving relationship between theory and observation in modern astronomy. Throughout history, these two approaches have engaged in a productive dance. Observations reveal unexpected phenomena that demand theoretical explanation, while theories make predictions that guide new observations. Many of the strangest stars we've discussed were first predicted by theory before being confirmed observationally, from neutron stars and black holes to various types of variable stars. Others, like Thorne-Zhitkoff objects and quark stars, remain theoretical possibilities still awaiting definitive detection. This ongoing dialogue between what we can imagine and what we can observe defines the frontier of astronomical knowledge. The strangest stars also serve as cosmic laboratories for testing fundamental physics under conditions impossible to recreate on Earth. The extreme gravity near neutron stars allows astronomers to test Einstein's general relativity with remarkable precision. The dense nuclear matter inside neutron stars provides insights into quantum chromodynamics and the strong nuclear force. The particle jets from black hole binaries accelerate matter to nearly the speed of light, testing special relativity and plasma physics. The synthesis of heavy elements in stellar explosions helps validate nuclear physics models. In these natural laboratories, the universe itself becomes our most powerful experimental apparatus, complementing and extending Earth-bound research. Perhaps most profoundly, our journey through strange stellar phenomena reminds us of the remarkable fact that we can understand these distant objects at all. Stars lie trillions of kilometers away, at temperatures and pressures wildly different from our everyday experience. Yet through careful observation, mathematical modeling, and the application of physical laws discovered here on Earth, we can comprehend their inner workings with astonishing accuracy. This comprehensibility of the universe, the fact that distant stars follow the same physical laws we measure in terrestrial laboratories, suggests a deep underlying unity to nature that transcends location and scale. This comprehensibility isn't just a philosophical curiosity, it's a practical necessity for our technological civilization. The nuclear fusion processes we're working to harness for clean energy mirror those occurring in stellar cores. The radiation we use for medical imaging and cancer treatment follows the same principles as the emissions from neutron stars and black hole accretion disks. The global positioning system that guides vehicles around our planet depends on relativistic corrections, first verified through observations of binary pulsars. Our understanding of strange stars translates directly into technological capabilities that improve human lives. Yet despite this impressive progress, we must acknowledge how much remains unknown about even the strangest and most studied stellar objects. We still don't fully understand the equation of state for neutron star matter, the mechanisms that launch relativistic jets from black hole systems, or the precise pathways by which the heaviest elements form in stellar explosions. Thorne-Zhitkov objects, quark stars, and strange matter stars remain theoretical possibilities without definitive observational confirmation. Some variable stars exhibit behavior that defies current models, while vanishing stars present puzzles with multiple possible explanations. These persistent mysteries ensure that the study of strange stars will remain a vibrant field for generations to come. Looking toward the future, our capacity to observe and understand strange stellar phenomena stands on the cusp of a new golden age. The James Webb Space Telescope peers into star-forming regions and distant galaxies with unprecedented clarity. The Vera C. Rubin Observatory will soon begin cataloguing billions of objects, including countless variable stars and transient events. Next-generation gravitational wave observatories will detect thousands of black hole and neutron star mergers annually. Advanced computer simulations will model stellar processes with increasing realism. Each new observation and calculation brings us closer to answering long-standing questions while inevitably raising new ones in the process. Beyond their scientific significance, strange stars have captured human imagination and inspired art, literature, and culture. Pulsars featured in science fiction long before their actual discovery. Black holes serve as metaphors in poetry and central plot devices in films. The apocalyptic brilliance of supernovae appears in paintings and music. Even speculative concepts like Dyson spheres have jumped from scientific papers to popular culture. This cultural resonance reminds us that astronomy connects not just with our intellectual curiosity, but with our deeper human needs for meaning, perspective, and wonder. This sense of wonder is perhaps the most valuable gift strange stars offer us. In a universe that often seems indifferent to human concerns, these cosmic wonders remind us of the extraordinary privilege of consciousness, of being the part of the universe capable of contemplating itself. When we observe a neutron star spinning hundreds of times per second, we're not just detecting radio waves with our telescopes, we're the universe becoming aware of its own astonishing creativity. When we calculate the conditions inside a quark star, we're not just solving equations, we're the cosmos reflecting on its own nature and possibilities. Strange stars also provide a humbling cosmic perspective. The energies involved in a gamma ray burst from a collapsing hypergiant star or a black hole merger dwarf anything our civilization can produce. The timescales of stellar evolution, millions and billions of years, make our individual lives and even our entire species' existence seem momentary by comparison. The sheer distances to these objects, measured in light years, the distance light travels in a year at 300,000 kilometers per second, emphasize the vastness of the cosmos relative to our tiny planet. This perspective doesn't diminish human experience, but enriches it, placing our lives within the grand cosmic context. Yet alongside this humbling perspective comes an empowering realization. Through scientific inquiry, we transcend our physical limitations. Though confined to a small planet orbiting an ordinary star, we've developed the intellectual and technological capabilities to understand phenomena occurring across billions of light years, and in conditions we could never directly experience. We've detected particles produced in neutron star collisions that occurred before humans existed. We've measured gravitational waves from black hole mergers in distant galaxies. We've traced the life cycles of stars from birth to death, despite their lifespans far exceeding our own. This cognitive reach beyond our immediate surroundings represents one of humanity's greatest achievements. As we conclude our exploration of the strangest stars in the cosmos, we find ourselves at a moment of extraordinary opportunity. We possess observational tools our scientific predecessors could only dream of, computational capabilities that enable increasingly sophisticated modeling, and theoretical frameworks that synthesize information across disciplines. Each strange star type we've discussed, from neutron stars to hypergiants, from vanishing stars to black hole binaries, represents not a final answer, but an open door to further discovery. The questions these cosmic oddballs raise will keep astronomers, physicists, and curious minds of all kinds engaged for centuries to come. The journey of discovery continues with each new observation, each refined theory, each moment of wonder when we contemplate the night sky. The strangest stars shine not just with physical light, but with the intellectual light they bring to our understanding of the universe. They challenge us to expand our thinking, develop new tools, and collaborate across disciplines. They remind us that the cosmos contains phenomena far more extraordinary than we might have imagined, yet still accessible to human comprehension. They connect us to the larger universe in which we live, revealing both its alien strangeness and its fundamental kinship with our own existence. So as we gaze upward on clear nights, or examine astronomical images, or read about the latest discoveries, let's remember that the strangest stars represent not just scientific curiosities, but windows into the fundamental nature of reality. Each peculiar stellar type, from the confirmed to the theoretical, from the merely unusual to the truly bizarre, adds another piece to our growing understanding of cosmic processes. Together, they reveal a universe of extraordinary diversity, dynamism, and interconnection, a universe where matter and energy explore every possibility permitted by physical law, and where conscious beings like ourselves can discover and appreciate the resulting wonders. From the crushing densities of neutron stars to the unstable brilliance of luminous blue variables, from the ghostly pulsations of variable stars to the deadly dance of stars orbiting black holes, the strangest stars in the cosmos invite us on a journey of perpetual discovery. They remind us of how far our understanding has come and how much remains to be explored. They connect us to the past, present, and future of the universe itself. And perhaps most importantly, they inspire us to keep asking questions, to keep looking deeper, and to keep sharing the wonder of cosmic discovery with each new generation. For in the final analysis, the strangest and most wondrous phenomenon in the universe may be the fact that the universe has produced beings capable of contemplating and understanding stars at all, a recursion of cosmic beauty that makes all our astronomical adventures ultimately journeys of self-discovery as well. As we part ways, consider that somewhere in the vastness of space, neutron stars are spinning with perfect precision. Luminous blue variables are preparing their next spectacular outbursts. Vanishing stars are puzzling distant observers. Binary stars are exchanging stellar material in cosmic dances, and countless other strange stellar phenomena are unfolding according to the elegant physical laws that govern our universe. The cosmic show continues whether we watch or not, but how fortunate we are to be the audience that can not only witness, but understand these extraordinary stellar performances. The strangest stars in the cosmos await your continued curiosity in this greatest of all ongoing stories. The evolution of our universe and our understanding of it